Mic 3 online. Mic 2 online. Mic 1. Hey, Padam.
Hello, everyone. We'll be starting in a few minutes, so if you could just take your place, that would be great. For those of us joining online, we'll be starting in a few minutes, so just keep your ears open. Thank you. Hello, everyone, and welcome to our 2023 version of the Partners Symposium on our second day. Today, we have a lot of speakers lined up. Very excited to hear all of them. I'm Charles, by the way. I'm coordinator in the partnership team here at Mila. Before we dive into our lineup of speakers, I would like to begin by acknowledging that Mila is located on unceded indigenous land. The Gagungwage nation is recognized as the custodians of the lands and water on which we gather today. And the Jojagwe, or Montreal, is historically known as a gathering place for many First Nations. Today, it is home to diverse populations of Indigenous and other peoples. We respect the continued connections with the past, present, and future in our ongoing relationship with Indigenous and other peoples and within the Montreal community. Mila acknowledges the systemic barriers that Indigenous peoples face with respect to education, employment, land, and technology. Indigenous knowledge and science have typically been devalued, excluded, and erased from AI science, and we therefore recognize the need for a commitment to work with Indigenous peoples in AI research and science. Thank you very much. This event is a great testament to open science research and scientific collaboration, embodying Mila's mission to develop AI for the benefit of all. We hope that the work being carried here at Mila continues to contribute to broader representation, inclusivity, and democratization of AI landscape. Before we start, a few housekeeping notes. If you do have questions during the day, we would ask you to ask them at the end of the talks, but you can still line up at the mic right here on my right and your left to ask the questions at the end of the presentations. If you are online, we have a Slack channel that is available and should be available. It's at the front, but you've also been sent the link in the last few days to join. You can ask your questions directly from there. We will have moderators looking at it and asking the questions in the room if you do send it. Very quick indication, restroom is up on the right. If you do have to leave or use the doors, please be mindful of the noise while closing or opening the doors that we're using. But except for that, I think everybody should be fine. I would like to welcome, first and foremost, for our opening words, Valérie Pisano, that is going to be talking to us from home. We thank Valérie for everything she's done for us in the last few years. We're really excited to have her with us, and I think she's going to have a lot to tell you in the next few minutes. Valérie, the floor is yours.
Hi, thank you, Charles, and good morning, everyone. And apologies for the sunshine, but I guess that's not the right way to start. It's wonderful that it's so sunny this week and a beautiful beginning to this part of the year. I'm very sorry I can't be there in person, but I have to say I'm quite honored that we're hosting this event again this year. And not a lot of people know this, and we didn't do a good job of highlighting it, but Mila basically celebrated its 5th anniversary a couple of weeks ago as a non-for-profit Quebec research institute in AI. And it's quite humbling to look back and think about what the vision was and what we were able to create with you all over the course of these 5 years. And some of you, I appreciate, were partners from the get-go, and some might have joined a couple of weeks or months ago. But the vision for Mila was quite interesting. We envisioned an institute that would not be a university, right? Mila is not a university, but would have the DNA of scientific curiosity and really push for discovery and advances in AI. You're going to be talking a lot about that today. An organization that would not be a private company and would not be all about the commercialization of AI, but would be very involved with industry and with partners. And today we have over 120 partners that have given us the privilege of being in this conversation with them around what AI might mean for their products, their services, and their processes. And then we're not a think tank per se, but we've picked a couple of topics where we bring together different kinds of leaders and we collaborate internationally, namely on the question of governance of AI. And we have the privilege of then sharing that with the rest of the world. And I know that there's been a lot of media recently about the promises and the perils of AI. But I think it's important to acknowledge that beyond the recent events and letters and headlines, Mila has been dedicated to these questions for many years. In fact, just before ChatGPT and everything else hit the newspapers, we had published with UNESCO a pretty thorough piece of work around the blind spots of governance and AI. And so I just want to acknowledge that these are three very unique components: scientific advances, collaboration with industry, and then thought leadership around the use and impact of AI in society. And we've created together, with your help, an organization that sits at a very interesting intersection point between the three, which gives us a vantage point that is quite unique, especially in the world that we're in today. So I wanted to name that, recognize it, celebrate where we are today. I'm always super impressed when we pull up the agenda for these sessions, both in terms of who are the participants and then what are the topics we're talking about. It's quite mind-blowing, and I'm really honored that we're hosting this again at Mila and in Montreal. And I just want to end by saying that in a world where AI is moving very quickly, where your organizations or your business are having to grapple with all the, again, opportunities of this going forward, I really do hope that the next 5 years and months and weeks are very much in the spirit of what we did up to now, which is a spirit of co-creation. So as you all figure out what AI might mean for you and what's exciting and or unnerving, we really want to continue the conversation with you as a privileged partner to say, okay, is there a role for Mila here? How can we help? How can we evolve how we think about our partnerships with you all so that we're adding value and building this technology into our lives in a very positive way? So that is what I felt compelled to share with you all this morning. Again, I'm sorry I can't be there for the actual talks, but I know you have a wonderful program and you'll be in very, very good hands. On that note, I'm looking for a cue from Shao. Shao, are we good? Am I introducing our first speaker? We are. Okay, there we go. All right. So let me just pull this up so I don't mess this up, because you're kicking off the day in quite unique fashion. So it's my honor to present our colleague Danilo Zoc, who's an associate member at Mila, associate professor at the Department of Biomedical Engineering at the Faculty of Medicine at McGill University. Right? AI is intersecting with so many disciplines right now. He is a medical doctor and a computer scientist. Why not? Why not do both, right? With a dual background in systems of neuroscience and machine learning algorithms. He's been named a Rising Star Scientist, yes, by the Bill and Melinda Gates Foundation in 2018. And last year again, because he's still quite young, was recognized as one of the top 5 Rising Star Scientists in Canada by research.com. So I've said probably more than enough to make him blush. And today, Danilo will be sharing with you some of his latest research about leveraging ML paradigms for single subject prediction. Danilo, the floor is yours. Have a great day, everyone.
All right.
Everybody can hear me? All right, so thanks so much for the very generous introduction. Danilo Stock, that's pronounced stock as in stock market. And so my research team at McGill and Mila really has the mandate to revisit classic questions in neuroscience and health using, oh, am I sharing this one? Okay, sorry for the remote people. Well, I shared the screen. This is this one.
Okay.
And so this is there. Okay. So mandate, revisit classic questions in neuroscience and health using emerging machine learning solutions. And that the way we do this is we typically wait for large data sets that didn't exist, that are wider, deeper, richer than what existed before. And then we go in and try to find new ways to attack classic questions from completely new angles. And that is why our research is very wide, and colleagues ask me regularly at cocktail parties what I'm actually doing. So you see some of these examples in 3 different themes on the following slides. So I talked to and compensated by different companies. So why is this intersection of health neuroscience, machine learning particularly attractive now? So what may be clear or not to people in this audience is starting on the left, the highest number of PhD positions funded in absolute numbers is probably in neuroscience. Why is that? So when I finished medical school 10 years ago, there were hardly any large data sets that existed, let's say more than 1,000 people rich. And it was the beginning of these international research consortia. So the European Brain Project started, $1 billion, no, well, that's in French, $1 billion just for research. Then there was a similar development in the United States. And other countries followed up, Japan, Israel, and so on and so forth. And that led to a wave of titanic data sets that we have now, just 10 years later, but oftentimes not so clear, what do we actually do with these massive data sets? And this is where machine learning comes in. So in a parallel development, around maybe 10 years ago, there is this exponential rise in interest and activity in the machine learning space. I show you the plot here with the increasing number of submissions to premium machine learning conferences every year, and that keeps being the case. And of course, those methodologies that come out of the machine learning space, they are exactly what we need to tackle some of these massive data sets that emerged in health and neuroscience. And that really opens the door to a new era in precision medicine or personalized medicine. So why am I saying that? First off, it's interesting to consider that until around 1900, if somebody went to a medical doctor, the life expectancy of that person increased maybe. So I think it's not really clear to the general public that it's just over the very recent decades that medicine started to be evidence-based, driven by data. Randomized clinical trials only emerged in the 50s. So it's not that long that it really have very principled and data-based ways of deciding how to treat a certain disease, treat a certain patient. And so this premium tool, let's just take randomized clinical trials, is based on a case control notion. So there's this binary approach. You have 2 different groups. There's the disease group and the healthy people. And this is what a lot of the knowledge has been derived from. The next step in the 21st century, however, is perhaps maybe to make precise statements about single individuals, the patient in front of you, which is entirely different from this case control setting that we have been in health, including neuroscience, over the last decades and still today. So let me give you an example from what this roughly means in the example of mental health. So a lot of these diseases that we diagnose and treat in mental health here on the left they don't really, as we say, carve nature at its joints. So what this means is that the labels that we have, they are not actually capturing the phenomena that we're actually trying to capture. So, and this is exactly where machine learning shines, because this is a regime of quantitative modeling where we can just put together all these very different, very diverse, complementary views on a same individual, bridging across genetics, life experience. We do studies of thousands of variables of behavior in thousands of families, for example, brain measurements and so forth. We can put all this together and ask machine learning algorithms for us to find meaning and see deeper into these very high dimensional descriptions of single individuals. And just to say this again, just 5 or 10 years ago, we did not have any of those data sets. They just didn't exist. So using this panel C now, we can hopefully get a cleaner description, biologically valid descriptions of disease entities, which would be just a milestone in itself, because that is a necessary prerequisite to then make earlier detections of certain diseases and conditions, try to anticipate what types of treatment may be ideal for a particular person. Let me just emphasize, in mental health, if somebody is suspected to have or diagnosed with something like major depression, you just need to realize that it takes 2 or 3 months to find a treatment most of the time, and it doesn't work in all the cases. It's a trial and error type of approach. So anything that allows us to go away from this will probably be progress in the future. So, and also we may be able to monitor progress using these clear descriptions to, in the end, enable precision medicine by single subject prediction. Okay, so 3 themes of how machine learning helps to make progress towards this goal. So the first is the idea of transfer learning. Let me just give a very simple definition. Oftentimes it means for us, we learn structured knowledge from a large data set that we then carry over to a smaller data set to more effectively mine the smaller resource. So even today, a lot of clinical data sets, they have sample sizes of only in the hundreds or thousands of people. So that is very different from the internet scale regime in which we're in computer vision, convolutional deep nets, or as we see now in large language models. So how can we do this? In this example here, in this paper 5 years ago, we combined pretty much all the brain functional imaging data sets that were out there at the time here on the left. And we tried to fit a deep learning algorithm that tried to distinguish dozens of different activities that people executed in the brain imaging scanner. And so the reason for why we did that is because we wanted to derive a functional atlas of what the territories are in that populate the cerebral cortex of the human brain across completely different task data sets. And so once you have this export product of this project, you can use this to slice and dice data in smaller cohorts, for example, clinical ones that are very hard to obtain. So and this gives you more statistical power for whatever the downstream analyses are. We also try to use YouTube to improve predictions based on brain scans of phenotypes in humans. So why YouTube? If you think about when a radiologist is trained, they already experienced the world in a quarter century. So somebody doesn't start radiology training at 5 or 15, but in the mid-20s usually. So there's already the visual cortex of those future radiologists has already experienced all these different categories in the natural world. And by the same token, why not fit convolutional deep nets on thousands of videos that have nothing to do with the brain, have nothing to do with the types of phenotypes that we ultimately want to predict. And that actually turns out to work in a number of cases. So we can take deep nets that have been pre-trained on pretty much the entire YouTube and then fine-tune them to really identify the patterns that are specific in brain scans, what a radiologist would see, to then make more refined predictions in these 40,000 individuals. So, and at the time, this was the largest existing brain imaging data set in the world. So my favorite transfer learning and last example is this one here. So let me explain this a little bit. When a psychiatrist, child psychiatrist sees somebody, a child who may have autism spectrum disorder, ASD, the way this works is that the children usually see this medical doctor several times because often it's not possible from a single session to be really sure that a certain child is diagnosed with this condition or not. So what we did here is we really just take the handwritten hospital reports in French, we digitize them, we translate them to English, we clean them to then use them for large language models. These large language models that we use, they have already been trained on millions of reports, on also thousands of articles from the scientific literature in psychology, medicine, and so forth. So there's all this implicit knowledge and semantic understanding of psychology and mental health and medicine that's already embedded in this learning architecture. We then carry this over to, and let me just give the extreme example, let's say 300 reports of the first visit of a child, in all cases of which the medical doctor did not yet know whether he or she will diagnose this child with autism. And the classification accuracies that you see on the left, they are first only. It shows that in 75% of the times, we can predict just from these text reports correctly whether the medical doctor will diagnose this child as autism in the future or not. So there's something about these cues that are in these text reports that is indicative of these features that are relevant to make this diagnosis. And just as a side note, these accuracies, they're actually better than the accuracies that we see based on high-dimensional brain imaging, which is very expensive, or based on genetics, the last 15 years also haven't given better prediction accuracies. So despite all this technology that we have, the most valuable source to make accurate predictions in this particular condition, at least, at a single subject level, may be the clinical intuition and machine learning, the clinical intuition of the psychiatrist, the domain expert itself. Okay, second example is diversity-aware modeling. So when me and my colleagues, we saw these always larger data sets, we were excited and we thought, wow, our prediction accuracies are gonna get better and better and better, and we'll now finally have the resources to really make concrete steps towards single subject prediction. That's not how the story went. The opposite was the case. So what you see on the x-axis, as we had always larger data sets in brain imaging and mental health, the prediction accuracies across various conditions, that's the colors, actually went down. So there's something about these always more representative, always larger, always less inclusion-exclusion criteria restricted data sets, as we get closer to the actual general population with less artificial case control and healthy groups, it actually becomes always more difficult to actually predict accurately at the single subject level. So we try to understand this better. With collaborators in Singapore and other parts of the world, we looked at two of the largest data sets at the time. And what we did is, across a number of phenotypes related to mental performance that you see on the x-axis there, in children on the right and adults on the left, we fitted models on the entire general population and then applied them in two groups. And that's in green, the white Americans, and in blue, African Americans. And what you can see in all these plots is in pretty much all cases, these predictive models perform much less well, statistically significant less well than the white Americans in all cases. So fitting a model on the largest existing data sets that exist in this space does not allow to make equally well-performing predictions in these different demographic groups. So we try to come up with a way to probe this in an experimental fashion. So and the way we do this is we use a causal inference framework from epidemiology that has not been used in neuroscience as far as we know. And what we do is we purposefully sample for our training sets in the cross-validation schemes specific degrees of specific demographic strata to see how this impacts the training and the prediction quality of the algorithms. So as a side note, this is what you see on the right side. The most used deconfounding techniques to correct for site differences, demographic differences, socioeconomic differences, they do not actually work, at least for out-of-sample prediction in machine learning. This is what we have shown in this paper. So it's not just the prediction quality. So what you see here is we look inside of these predictive algorithms and we quantify how changing diversities, changing demographic composition, stratification in our training cohorts, how does this actually affect what these predictive algorithms latch onto? And look at the scaling there. So we go down all the way to 0.6, 0.5 similarity in the predictive principles that these learning algorithms have detected and extracted. So what type of demographic strata are part of your training sample has a huge impact on what the machine learning algorithm actually identifies as relevant for prediction. So, and it's not just that, it gets even more complicated because across the input space, in our case, across the cortex, what features are affected by diverging diversity in the training cohorts is not uniformly distributed. So in other words, there are certain parts of the brain that disproportionately change more, yield more brittle predictive principles than others. So and it turns out that it's the highest evolved parts of the brain, the most recently expanded compared to monkeys, 30 times bigger. It's those parts of the brain that actually keep maturing through adolescence, through early adulthood. It's those parts of the brain that are live wired, maybe a unique aspect of our species. It's those parts that actually give the most brittle predictive principles. And so this is something that we probably need to take into account in the future. Okay, last theme to finish up. Oftentimes, I talk to students and they want to use the latest and most amazing tools. And the question that typically comes up then is, can we actually use this tool that is really hot on Twitter right now for the types of data sets that we actually have that actually exist in our particular space? So I think what we need is careful empirical scaling analyses that benchmark and quantify the feasibility of which regimes of analysis paradigms are actually beneficial for certain predictions. So we conducted the largest deep learning benchmarking study in brain imaging neuroscience a couple of years ago, and we pitted against each other standard linear models in red, nonlinear extensions of those in green, and then hierarchical nonlinear models in blue. And we conduct what's called an empirical sample complexity analysis, where we act as if we had less subjects than we actually have to scale the prediction performance as a function of the cohort training sample size. So, and on the left, you see the scaling. That's the textbook results that everybody would expect. Deep learning models do better than last generation kernel nonlinear methods. And these are doing better than the standard linear models in red. And that's the case pretty much in all sample sizes. That's not what we observed in brain imaging data. This is what you see on the right. So we used the largest existing brain imaging data at the time. This was at the time 10,000 people. We see a collapse of these modeling regimes. So just based on this slide, you can say the scaling behavior of these algorithms in these kind of medical data, they are just not the same. We cannot take these insights from the ISML NURBS community and just carry them over to the medical field. This empirically shows that that's probably not possible. So we then tried all sorts of feature selection techniques, not going to go into details. So we tried to attack these data from all sorts of different perspectives. We did not see a lot of divergence between the linear, the nonlinear, and the hierarchically nonlinear modeling regimes in our scaling analyses. And so here's some clues why that may be. We then went back to this benchmark data sets from the machine learning community here on the left. And we deliberately added noise to one of the favorite data sets that people look at, the MNIST data set. And what you see across these panels is as we add always more noise to the machine learning data set, we see this collapse of these modeling paradigms exactly as we saw in the medical data. So that's not a definitive proof, but it shows clues that noise may be part of the reason why, just imagine an X-ray and imagine a natural image of a dog. There's just a difference in the quality of detail that we have in these kinds of data. So, but here's some positive news. We collaborated with people at Charité Berlin, used even larger brain imaging data sets that merged in the meantime. And we tried to extrapolate towards sample size of 1 million people. And we do see small increases in the prediction performance in this very large modeling regime, in this large sample regime, sorry. But the question is, of course, as a society, do we want to pay? Do we really want to stem this logistic effort to get increases of a few % of accuracy? Is this really necessary? So this concludes my third theme of examples of studies that I run in my lab. And I hope I convinced you that there is value in putting machine learning solutions to questions in neuroscience and health. We can oftentimes not use those tools out of the box, just download it from GitHub and apply it to the medical data set. That's not how it works most of the time. There's a lot of work that's necessary to adapt these core machine learning contributions to the domain questions that we really have. And so, however, if we succeed in doing this, we could go beyond this classic case control binary setting that has served us well to make progress towards single subject predictions that would be faster, more cost effective, and more pragmatic. So I thank my partners and I thank these institutions for the financial support. Okay, any questions?
Thank you very much, Danilo. I just have a quick question for you on the end, because you mentioned that it's difficult to take an out of the box and have that solution. But if partners would want to interact with some of the research that you're doing or learn how to kind of have those steps, how would you go about, or how would you suggest to them to work with?
How to do this?
Yeah.
I think in my limited experience, you need a tailored approach. So for each data set, for each research question, it's different. So this is why, just very concretely, in my lab, we have a completely different analysis pipeline in every single project. So the way we try to do it, our approach is to be a little bit the spider on the web. We collaborate with domain experts who have 20, 30 years of experience in a certain area. We can speak their language. We work with core machine learning experts. We can speak their language too. And we kind of mediate, having two caps at the same time, wearing two hats. We try to mediate between them to kind of ping pong back and forth, iterative solutions towards something that, in my experience, is most of the time tailor-made.
Thank you very much.
Okay. Thanks so much.
Thank you very much, Danilo. So I think we'll be hearing Guillaume also talk a little bit about a similar or related subject. So we'll be able to have a lot more on insights on neuroscience and ML. For now, next up, we're going to be welcoming Bruno Rousseau and Pierre-Luc Saint-Charles for their presentation on one of the types of collaborative projects we do with partners, the AI applied research projects. It's one of the ways that many of our partners work with us more concretely on collaborative projects. More specifically, we will hear them on developing models at the intersection of deep learning and geoscience. It's an applied NRCan, so Natural Resources Canada, and AMLRT, Applied Machine Learning Research Team, project case study. Bruno and Pierre-Luc obtained their PhD in 2008 and 2018 respectively. Bruno studied condensed matter and material physics and then worked as a data scientist in a consultancy firm And Pierre-Luc studied computer vision and image processing and then worked as a postdoc in Montreal-based Research Institute. Both joined Mila's applied machine learning team as research scientists in 2019 and have since worked on geoscience projects with the team. So Bruno, Pierre-Luc, the floor is yours.
Good morning. Thank you for that great introduction. So today, Pierre-Luc and I will present our team here at Mila, and we will do so in the form of presenting a project that we have ongoing with NRCap. So first, we'll introduce the Applied Machine Learning Research Team, which we like to call AMLERT. It's not a city in the north of Canada, it's our team. Then we'll discuss what a typical pipeline looks like when we have a project in collaboration with a partner or a client. And then we'll dive in a little deeper on that project we have with Natural Resources Canada. Their expertise that they bring to the table. We'll summarize a little bit the data that they brought to the table, what our mandate was, and the outcome of that project. So first, our team. We are a team composed of 18 research scientists. We are led by 3 managers with a combined experience of over 40 years in machine learning and deep learning. We cover a wide range of machine learning and deep learning expertise. Of course, natural language processing and large language models, which are all the rage these days. We also have extensive expertise in computer vision. But what is perhaps a bit unusual is we also have a diversified team with expertise across the board in perhaps more unusual domains for deep learning. So whether it's fraud detection or time series forecasting, the types of topics that are often of critical importance for companies, but that are perhaps less touched upon in academia. But we have a lot of experience with these kinds of projects.
So one thing we could also highlight here that's actually fairly interesting is that everybody in our team has a totally different background in a way. We have physicists with us that are helping us try to deal with problems that typically just as computer engineers and computer scientists, it might not be easy to solve them, but this is actually something that's actually very useful, unique, and actually required for our type of work, because we work at the intersection between different domains. And in this intersection, we need to have a wide variety of perspectives to try to tackle each problem.
So what are the kinds of services that our team can offer partners? On the one hand, we have our collaborative research projects, which are really hands-on. Typically 2 team members led by one of our managers will really get their hands dirty and produce a full-fledged solution. We can work with confidential data if need be. We can leverage the computational resources of our partners, whether they be on-site or in the cloud. We like to first, of course, identify what is the highest value problem that can be tackled with a partner. And we can really tackle difficult and niche problems. As was alluded to by the previous speaker, it's often necessary to tailor-make a solution to a complex problem. So that's really where our team shines. A key point in the projects that we take on is the relationship that we build with domain experts that are employees of our partners. It's really, really important that we have ongoing conversations with these domain experts to make sure that the project stays focused on the highest possible value, right? We are very knowledgeable across a wide variety of fields, but still we must have input from domain experts to make sure that we're headed in the right direction. Our goal also is to transfer the machine learning knowledge that we've acquired throughout the project to the clients. We are not product vendors. Our goal is not to just create a solution and walk away. Our goal is really to transfer the knowledge and the solution so that the partner can own it and leverage it in an ongoing fashion. Our typical projects, since we're talking about complex topics, typically it's 12 to 14 months. and there is access to funding to cover a significant part of the cost. Another aspect of what we offer is more consultation or training. So these typically will last over a 4 to 6 months period, and one team member will offer what we would call more like a coaching or service, offering about 25 to 50 hours to a company. So we support industrial research and development projects where what we offer is really guidance, tips, and making sure that the protocol established in collaboration with the company is robust and sound.
Well, one thing also that we could highlight that's actually interesting here is that our team does not focus at all on productization. It's something that's actually fairly unique. So we stick to proof of concept development. And when it comes to actual productization, we assume that the knowledge we transfer is really the scientific part for maintaining, just maintaining the experiments, developing new models, things like that. But in the end, we do rely on clients to be able to productize their own models.
So today, we will focus on our project with NRCan. We'll briefly dive into the project pipeline that we put together in collaboration with our partners. And we'll summarize the data that was available for this project and what our mandate was. So our collaborators are affiliated with the Geological Survey of Canada, which is a branch of Natural Resources Canada. Funny fact, the Geological Survey is older than the country itself. So on an unrelated topic, the research scientists we work with there have a lot of experience. And so they really are world level experts in geology and seismology, but they wanted to know if we could bring in some deep learning and machine learning to their workflow to improve the efficacy of their work. And so when they came to us, they really had this one data set that's centered around the Lalor mining camp, which is a mining camp that's on top of a so-called volcanogenic massive sulfide ore deposit. So that's basically a gold and zinc and copper mine. And the data that they have at this site is pretty unique, pretty unusual. On the one hand, they have seismic data represented by the image at the bottom of the slide there. So essentially, this is obtained by using essentially dynamite to create shock waves in the earth and measuring those shock waves at the surface of the earth with little sensors. And the imagery that you can extract from these kinds of measurements is akin a little bit to an ecography, right? When a doctor uses ultrasounds to visualize a child in a mother's womb. So it's indicative of where the interfaces are, where we go from one type of rock to another. But as you can see, it's a pretty ghostly kind of source of information. It doesn't tell us exactly what's there. It basically tells us where there are changes or interfaces between rock types. They also have access to all of these borehole data, which are essentially carats dug deep underground. And as you can see here, these spaghettis kind of tell us a little bit the kind of rocks that are there. So every different color that you can see on this image corresponds to a rock type, red being the ore, right, where the money is. And so what we end up with this data set is a sparse 3D point cloud of rock class types. And it's not very uniformly sampled. Of course, they dug closer to where they initially thought the ore would be, and it gives us incomplete, noisy information about what's under there. So when they approached us, they were wondering, can we use this information in order to create basically a map of the underground? So the inputs would be this seismic data and some of the borehole data in order to produce basically a complete mapping of what is the rock type at every point underground around this mine. To be clear, the image that you can see at the bottom of the slide there is the kind of models that they can already produce by using only the borehole data, right? It's basically a sophisticated interpolation. That approach does not leverage the seismic data at all. So the real question is, can we leverage this seismic data in order to produce maps that are even better than what they can already do? And that could be a very interesting question to answer. It can have very important economic impacts because digging these holes is extremely expensive. Creating a seismic survey is also expensive, but for the price of 1 or 2 extra boreholes, you can have a seismic survey. So if it's a game changer that can really help understand what's underground, then there's potential economic benefits in the way of reducing the number of boreholes that are necessary. So we talked with them, and of course, we wanted to propose, develop, and train models to do this. There were 2 aspects. First, to begin with, we started with a simpler task, and we helped them with the data pre-processing using computer vision-based approaches. And then we wanted to tackle this specific problem. Can we improve the map of the underground by leveraging that seismic data? So now we can say a few words about our pipeline.
Sure. So overall, one thing I'll probably try to highlight first is that this pipeline is essentially just a high-level description. Every project is going to be fairly unique, and we tend to iterate and maybe jump between steps a lot. It's really on a project per project basis. But for now, let's say this is an overview. So these are the different steps. We're going to go through them one by one and essentially try to highlight some of the key aspects that made the NRCan collaboration project unique. So first, the prerequisites. Of course, this is a machine learning project. Before we even step in, we need to make sure it's actually something we can solve, or at least we can provide some help with. The first step is really trying to identify whether the data itself is in sufficient quantity in order to be analyzed or processed. This is something that's really right off the start. In the first 2 to 4 months of the project, we need to figure out what sufficient actually means in this context. And this is, again, very unique for each project. For NRCan, it was actually quite challenging to figure this one out, but I'll get back to that in a moment. Next, the annotations themselves must have a decent level of quality and consistency. This is even just at the annotator level. If we provide the same data to 2 experts and they give us different annotations, there might be some trouble there. So this is something we really need to consider before we get started on the project itself. Then we must have access to the domain experts directly. We do not want to be in the dark in our own sandbox, trying to prove ourselves right, doing things that are illogical. So this is actually quite necessary. And in the end, the project itself must be a good fit for machine learning methodologies, let's say. There must be kind of a methodology that we can set up and try to use to actually provide interesting results. So for NRCan itself, the first thing we can note here is that we only had access to data for 1 mining camp. One thing that's interesting is we had synthetic data, which made the project actually doable, but we only had 1 mine. So in terms of trying to say, oh, we're going to apply our models across Canada and we're going to discover amazing minerals, maybe not. So this was something we needed to consider right up front. And then also one thing that's very interesting to note here is that the seismic data is noisy and incomplete. It does not give us a full picture of what's actually underground. It is still linked to rock unit interfaces, but it is something that is fairly fresh in the geology literature. It's something that was proposed as, hey, we could use this, but it wasn't totally 100% demonstrated in the past. So our ultimate goal here was really to try to do better than what geologists were already doing with fewer boreholes by leveraging the seismic data itself. Ideally, they just wanted a second opinion on the interpretations that they already had, so any kind of results were interesting to them. The next step is actually quite important for our own work. It's the domain understanding part. So we can split this into 3 steps, essentially. It's first, we do data analysis. So data analysis, the first step is really, okay, you told us the annotations are consistent and everything, but now we're actually going to go and dig into the data to make sure that's true. And in this case, it's really all about trying to figure out where the issues are. Next, we're going to actually analyze the distribution of the data. So in this case, try to understand how seismic data works, because we're really not experts in that. At least I wasn't. And in the end, we also want to identify anomalies and biases in the data so we can actually figure out the problems that we might encounter on the road to what we actually want to do. So for NRCan, the first thing that we can highlight here is that we did find numerous issues with the labels that were provided to us, especially in the seismic pre-processing part of the project. And in the coordinates that we had for the 3D boreholes, so the spaghettis in space, This was actually quite challenging to figure out that there were issues. We had to do a lot of back and forth, but this is something that's drastic and super important to figure out before we start working. And also, one thing that we wanted to do was try to figure out that seismic data is indeed correlated with rock unit interfaces. This is something that was quite fundamental, and Bruno was quite the expert in doing that. There was a lot of math involved, and I'm quite happy it was there for me. So in the end, the next step for domain understanding is really trying to understand what is typically proposed in the target domain. So this really goes through first, what do experts consider as their own baseline approach? What is their standard butter knife when they want to tackle this kind of problem? Then we need to figure out what kind of valuation setting are they typically using to say like, oh, okay, my approach is better than yours. We need to really understand that because it's never as clean as in machine learning where you have nice data sets that are prepared in labs. Then we need to really try to define what can be considered as an improvement over baselines. And this is something that's actually quite unique in the case of NRCan. So first, the baseline approaches for this project were Gaussian processes, so Kriging models. Again, I'm very glad I have Bruno with me because these models are quite funky. And in the end, just understanding them and trying to compare with them is quite challenging. Next, one thing that's very unique also is the fact that we have a single mine. We have data for a single camp. So we're not going to be trying to generalize our models across Canada. So how do we actually evaluate? Well, it's within this mine. Can we evaluate or try to generalize across space for this one survey site? And that's our ultimate goal. And then finally, as I said before, any kind of results that are usable as a second opinion for something that might be surprising to an expert is already something that's an improvement, a potential improvement, because they will go and dig and verify.
One thing that we learned speaking with them about this particular topic is that each mine is unique. It's its own little thing, and they will spend years and years and years in analyzing the same site. So there's immense value in providing a second opinion. So that's not something that we came to the project already knowing. We discovered that through our discussions with our counterparts at NRCan. They were very happy with just being able to produce anything on this one site. No need to try to predict for 50 mines.
Yep. Next, for domain understanding, essentially, we're going to dig through the literature, both in machine learning and in the domain itself, to try to understand first if there are tasks or benchmarks that can be used that have similar inputs and outputs. And then we're going to try to figure out if there are methods or techniques that can help with specific challenge related to the project. In this case, one thing we figured out was, okay, well, the kind of task that we have at hand is essentially semi-supervised binary image segmentation combined with some label propagation. This is something that we found that was linked maybe to, in microscopic imaging, cell segmentation. There was a few links there. So it's the kind of literature that we're going to go look through. And also for the techniques and the methods that can help us deal with this particular problem, domain adaptation was actually something that's quite needed in this case, just because we have synthetic data and we're going to try to apply it to real data. So yes, quite challenging. So the next step in our pipeline is really going to be to try to formalize the problem itself. So the first step in that is really trying to build an experimental protocol. So this is really just a high-level methodology for what we're going to do. First, we're going to try to figure out what's going to be ingested for our models. In this case, we do have funky data. It's images and sparse point clouds. So this is funky. Then what we're going to predict. Finally, how we're going to split the data. And really, there's a fourth step. It's trying to figure out how we're going to evaluate the actual predictions. So for NRCan, as I just mentioned, it's seismic reflection images and borehole data. So there's two modalities there. We already know our models are going to be at least multi-model. Then at least the predictions are just arrays. So that's good. It's arrays of class labels. The split itself, it's interesting. We only have one site. So essentially the boreholes or the spaghettis, we're going to split into different sets and try to have an expert do the actual split so we can evaluate based on scenarios. And finally, just use classic classification metrics to do the evaluation. Next in the problem formalization is really trying to figure out a research plan for the things we're going to work with in experiments and try to improve baselines upon. It's first, how will the model learn? Then it's the kind of model architecture we'll use. And finally, it's the kind of training approach. So there's a lot of variety there. This is mostly where we're going to contribute new state-of-the-art machine learning knowledge. So for the NRCan project, it was really, okay, well, we'll just use classic classification losses because, again, there's nothing fancy in doing classification. But For the model architectures, we're essentially in the end combining convolutional neural networks with graph neural networks. So there's some funkiness there. And we're going to use self-supervised learning to do pre-training of our seismic encoders and then try to do domain adaptation fine-tuning. So this is really where things are going to be a little bit more complex and off-the-shelf solutions that we can typically find in the literature. And this is where the expertise of our team really shines. For the experimentation itself, again, now that I will skim over this fairly quickly because each solution is really project specific and we don't have time to go really dig into the details of the NRCan project. But the first phase that we did, as Bruno mentioned earlier, is the seismic pre-processing. So this is a fairly standard computer vision pipeline where we take the input raw data and we do a little bit of processing, do predictions, and we come up with a result that's actually fairly interesting for our collaborators already. The second phase of the project was using the seismic data that's already been processed. We're going to try to detect the actual interfaces between rock units. So where rock A comes in contact with rock B. This is something that we started doing with synthetic data first, where we could have the full ground truth and everything that's underground. And then the third phase of the project is really trying to do label propagation. So knowing where the rock interfaces are and having the spaghettis floating in space, we're going to actually propagate the rock unit labels across the space and try to map out the whole mining camp. In the end, yes, this is still quite a difficult step, even though it's one that might be somewhat simple to explain. So now finally, in terms of reporting, each project is fairly unique again and again and again, but these are the main components of what we provide in terms of reporting. So a final report that provides a full description of the data analysis, methodology, experimental results, observations, everything that we can think of is going to be in a final report. Then we have a summary of ideas for future research, potential improvements and limitations. This is something that's actually quite important because we want our clients to really know what the limitations of the solutions we're bringing to the table are. Next, in terms of code, this is something that might also differentiate us from maybe more academic, let's say, contributors. It's that we will provide standalone experiment framework with a lot of latest like tools and modern tools and everything. And this is going to be high quality code with documentation, testing, all kinds of stuff. So it's going to be good and well done, along with configuration files that can allow you to retrain any kind of model and everything. For the models themselves, I'll just mention that we're going to have checkpoints that are easy to use and things that are actually tuned to be easy to use and good for your compute resources. So now, in the end, for the NRCan project, this is something we spread out over 2 years. So we did deliver a lot of things at the end. So for the project outcome for this actual project, so our hands-on work actually identified many challenges, including the fact that synthetic to real data adaptation is super challenging. So we actually had to develop a lot of new ideas in this case. The rock unit interfaces detected are always going to be imperfect, and this is something we have to deal with, but the uncertainty is part of the challenge of this whole project. And in the end, also doing label propagation with volumes that have 50 million voxels, it's really not easy. And yeah, so this is still ongoing work. We're tackling a lot of ideas in domain adaptation graph neural networks. If you've ever heard of problems that seem somewhat familiar to this, let us know. We'll probably recycle some ideas. And in the end, we did get a publication in NeurIPS 2021 workshop for a physical sciences workshop. So that was actually interesting because this publication has already been reused by many people trying to build and benchmark their own methods. And we're currently working on a journal extension for this. So this is it. If you're interested in collaborating, don't hesitate to contact us. We can definitely chat. It's always great just hearing about potential project ideas and everything. So thank you.
Thank you.
Thank you very much, Pierre-Luc and Bruno. It's interesting to hear that there's really something at Mila, and a lot of people share that, but Danilo mentioned it, and you guys mentioned it, the variety of disciplines that we can kind of cover, that we have domain expertise of, or that we can talk with, is really interesting. So don't hesitate to send us a message, especially for the types of projects that they do. It's great to hear from them every time. And yeah, so thank you, Bruno, and thank you, Pierre-Luc. So we'll be going on a small break. We'll be back in about 20 minutes. So there's still coffee, still pastry on the other side, and we'll see you in 20 minutes with Guillaume. Thank you very much. Hello everyone, bonjour tout le monde. Nous allons recommencer dans 2 minutes environ. Donc, si vous voulez prendre place ou revenir à votre ordinateur, si vous êtes à la maison, si vous m'entendez. Sorry about that. We will start in about 2 minutes. So if you want to come sit down if you're in person, or if you're home, if you can hear me, sit down in front of your computer, that'll be great. Thank you very much.
Mais ils veulent qu'on projette le
Thank you very much, everyone, for the break. I hope you enjoyed the coffee, the pastries, and at home, maybe you had them. I don't know, but up to you. So our next speaker is going to be Guillaume Lajoie. He is an assistant professor in the Department of Mathematics and Statistics at the University of Montreal and a core academic member at Mila. He is also a SciPar AI chair and Canada Research Chair in Neural Computation and Interfacing. He will be talking to us about ML for neurotechnologies. And his research group, more generally, works at the intersection of AI and neuroscience, or neuro-AI, developing tools to better understand neural networks, as well as algorithms for brain-machine interfaces, or scientific and clinical use. Today, as I said, he'll be sharing some research insights on ML and neuroscience, or neurotechnologies, I should say. Guillaume, the floor is yours.
Thank you very much for the great introduction. I have actually one correction to make, because starting from today, I'm now an associate professor. I got tenure today. So this is a
Congratulations.
Very happy about that. Now, okay. So thank you for the introduction. Thank you for coming. This is always a great pleasure to have like the broader Mila family come together and talk and share about these research endeavors. As was mentioned, let me see here. This should be working. Here we go. My broader research interests lie at the intersection of neuroscience and AI, right? And so fundamentally, I think there's very important questions that are common to both. Questions about computation, questions about intelligence. And I really think that this multidisciplinary interaction between these disciplines yields better understanding in both, right? And that's not just, getting inspiration from the brain to build better systems and using tools from AI to understand the brain. These things are fruitful, that's for sure, but there's really core common principles. And that's what my lab works on. And so a big part of my research is in theory and in learning theory in general. Part of that program is centered on applications, specifically applications towards neuroscience, and that's what I want to talk about today. So, if you're interested in discussing theory and a lot of these scientific discoveries, I'm happy to talk about this. Today, I want to focus on a more applied version of this sort of intersection, and that is about neurotechnologies. Right, so neurotechnology is kind of on the rise. Like if you just look at the news in this past week, for example, you might have seen two big headlines, right? So one of which is, brain implant helps paralyzed man to walk again. It's pretty cool. Another one is, as always, Elon Musk's sort of outfits making the news. So Neuralink gets FDA approval. This is just, signals that there's some progress, some fast progress in developing ways to directly interact with the nervous system. And although this is, seems like science fiction, and it kind of brings us closer to these types of ideas, I think there's tremendous opportunities beyond the obvious here, beyond just repairing motor control, so on and so forth. And I'll touch on this a little bit more, how neurotechnologies can replace a lot of the treatments in clinical settings and make clinical interventions more precise. So just usually, what do I mean by neurotechnologies or neural interfaces in general? Let's take the example of this news with this brain implant that made the news because it has a lot of these components. So usually it's technology that interacts in a closed loop with the nervous system. In this particular case, what the researchers from EPFL did is they implanted electrodes in the motor cortex of a paralyzed patient. They could read signals from the motor cortex of that patient, and then they use it to stimulate the spinal cord below the sort of break. So that's the patient that had an accident, lost the use of his legs, and then essentially building a digital bridge to control them, to help stimulate the spinal cord and then recover the use of legs. So the components here are kind of twofold. You need to read out information from the brain. So you need hardware to do this. I'll talk about this a little bit. You need to be able to decode these signals in a way that can translate this in volitional control of a stimulation, then that's the third component, into a control problem. Essentially, how do you reconnect with the spinal cord, right? So there's a lot of moving parts here, and you can imagine that a lot of these things wouldn't be possible without machine learning algorithms to help that pipeline. So I want to talk about a little bit of these progresses today and how we're involved in this field in general. And I want to note here that this general idea of directly interacting with the nervous system is not only for sort of motor diseases, right? Oftentimes, the nervous system regulates a lot of things in our bodies, and intervening at the nervous system can replace pharmaceutical interventions, right? Pharmaceutical interventions usually are kind of a big hammer, right? You take a pill, it goes everywhere in your body, even though you want to target a small part that is problematic. And so if you can target more, interventions that are more local, then you avoid a lot of side effects. So there's hope to use neural interfacing for a bunch of different ailments that are not just neurologically related in a sense, right? And I'll touch on this in a little bit. Okay, so some disclaimer. This talk will cover some sensitive experimental content, right? So we're talking about experiments that involves the nervous system. So I'll show some photos. If some of you are queasy, I'll wave my hands and you can cover your eyes for the slides that these are coming in. But things to note, there's no pain receptors in the brain, okay? And the brain is surprisingly robust and resilient. So when we talk about implants, know that there's very well-established protocols and that there's usually no pain associated with it, right? Okay, that being said, let's start from the start. So Danilo did a great job at motivating the neuroscience and the importance of neuroscience and this modern scientific field. And so let's take a step back really, and so we're on the same page. In the brain, information is processed largely by neurons. Neurons are cells that communicate with each other through synapses, right? So they're units that are connected with each other, and the synapses act as weights, right? And these interactions are mediated with electrochemical activity, like spikes, action potentials. And these form big networks akin to, obviously, artificial neural networks, and they process information. One thing to note is that evolution learned basically general recipes to wire neurons together and for them to learn functions, right? And as Danilo mentioned, some of the parts of the brain that are sort of higher up in the evolutionary hierarchy of humans are dedicated to learning, right? To like basically they're kind of useless at birth and then they learn a lot throughout development. And the same is true to a different extent in the sensory systems of many animals. And I want to make the point that the general recipe is pretty much the same across a lot of animals. And so that means that whether you're an electric fish or you're a rabbit, a lot of the sensory inputs you get from the world are integrated sort of like in the same way, right? There's neurons that integrate these signals. And so, you know, and you can repurpose these things. And there's evidence of this in nature, right? Blind people repurpose brains, visual areas for language. There's plasticity here that is the general recipe from evolution. And so that tells us that in principle, we should be able to write information to the brain and to read information from the brain pretty easily, in the sense that evolution has granted these solutions that facilitate this. So as long as you have a clean signal, the brain should be able to learn to interact with external devices, right? And so this is this paradigm that I want to explore today. Okay, so brain-computer interfacing, what does that eat in winter, like we say in French, right? So definition is essentially directly interact with the nervous neural activity in a closed loop paradigms. But why would we want to do this? Well, there's a few different reasons. First, as I kind of alluded to, there's medical applications, right? The development of prosthetics, to mitigate pathological neural dynamics, promote recovery, all topics I'll cover in examples today. The second, and I think that's a really important one, is that it's a magnificent scientific tool. It enables to probe and to interact with the nervous system to understand how brain circuits work, and helps us you know, ask scientific questions that go beyond usual experimental paradigms. And I'll quickly touch on this at the very end if I have time. And the third, of course, is you know, it changes how we interact with technology. You know, we can control devices in ways that we couldn't before, and so on and so forth, right? Okay, so how is this done, right? So when we say brain-computer interfacing, there's a big spectrum, right? And so I'd like to kind of put this on a map with two axes, like we do usually, right, to make this things overly simple. And so on the vertical axis here, I'd like to point out that there's basically two modalities. One is invasive, i.e. something that you need to get implanted, goes under your skin somehow. And the other end of that axis is non-invasive, a helmet you put on, like a bracelet, right? These are different ways to interact with the nervous system. And on the horizontal axis is kind of the way information flows. You can either input information in the brain, stimulate the nervous system, or read out information from the brain, decode from the nervous system. And of course, like in the examples I showed at the beginning, these two modalities are kind of used, right? Like you're recording and then stimulating in a bidirectional way. So there's like a host of different modalities along these axes, right? So on the input side, you can think about, in non-invasive, you can think about ways to stimulate the brain that don't require implants, like a transcranial direct current stimulation and TMS, which does this with magnetic fields. And of course, like all of the technology we use, right? Your phone, your computer is a non-invasive way to input information to the brain. You're using sensory inputs, right? And then on the output side, there's all kinds of technologies to read out information in the brain that's non-invasive. EEG, cortical hemodynamics, EMG, which are electrodes that read out activity from muscles. And of course, there's the big rigs like fMRIs and so on, right? And now on the invasive part of things, this is where it gets a little bit gory, but I think the important part to understand is that this is how to get the real, like true clean signals, right? There's a lot of noise in the non-invasive part of things. In the invasive part of things, the price to pay, of course, is to go through surgery, but you get really a lot more degrees of freedom to play with. So on the input side, there's optogenetics technology, which is essentially uses light to activate neural activity, microelectrode stimulation, and ECOG, right, which is a form of surface electrode that's on the surface of the brain, which is the modality that was used in the first example I showed. So this is kind of the landscape. So it's very multimodal and it's very active landscape for different use cases. You might want to use different modalities, and I'll touch on challenges that kind of address all of these modalities. But before going too deep, I want to talk about early history of brain-machine interface. And one could argue that one of the first time a brain-computer interface or brain-machine interface was created is in the 60s, actually, in this seminal paper from Eberhard Fetz, where he demonstrated through an experiment that is called operant conditioning, that essentially it's possible to control the activity of single neurons in your brain if you have feedback about that activity, right? This is a pretty cool experiment. So what happened is, there was a monkey that was implanted with an electrode in its motor cortex or sensory cortex, I think. And he was given, like, he was able to look at a dial that was giving it the firing rate of that neuron, right? And essentially the task was, if you match a target firing rate, you get a reward. Very quickly, the monkey learned to control the activity of that one neuron that was recorded from the brain to get that reward. So think about this for a second. That means that just by having feedback of what the firing rate of that single neuron is, you can learn to control that in a very volitional way. And this is reproducible across the board, right? Again, it points to the generality of the sensory motor type of cortical dynamics that we are all endowed with, right? These things, if you learn a task, you practice it, you get error signals, you suck at it for a while, and then you get it. You play tennis, like you get to hit the ball. Same is true if you plug in a different modality, right? So this was the first time this was shown, and this was in '69, right? So we've known this for a while. Fast forward now, there's a lot of neurotechnologies that are out there. Deep brain stimulation is a common treatment for Parkinson's disease. Cochlear implants are another type of implants that are quite used in treating sort of hearing disorders. These are always things that interact directly with the nervous system. And from the industry point of view, there's a rapid development of hardware. There's a lot of research in academia, a bunch of companies that are developing this hardware to make interacting with the brain and the nervous system more direct, right? So just an example, things are scaling up quite fast. The chip from Neuralink here has sort of 1,000+ recording channels, which is a far cry from that single electrode that was used in the '69 experiment. So this is an example. You might have seen this a couple of years ago, which is the sort of demonstration from Neuralink that shows a monkey playing Pong with the neural implant. Again, the idea is that the little rod that the monkey is holding here is just a reward. But the activity of the paddle in this Pong game is controlled with a neural prosthetic that's implanted in the motor cortex of the monkey, right? So you might have remembered this. So this little part here is controlled by the monkey that's learned to control it and learned to play Pong. It's quite astonishing. But when you think about it, this is actually the same thing as what was done in the '60s, right? It's 1 degree of freedom control of an external device, right? And so this was sort of the state-of-the-art demonstration of what we can do with these implants, but really there's not a lot that's changed into what's been demonstrated before, which brings me to my point, right? Our decoding and encoding capacities does not immediately scale with channel counts. There's a huge challenge into leveraging these extra degrees of freedom when we're talking about interacting with the brain, right? And so you might have seen other types of results like this, where a patient was implanted with a neural interface and motor cortex to control an external device. These types of early demonstrations heavily relied on primitives that were learned on the robotic side, right? So it's very light interactions from the nervous system. In other words, it's not like that lady is controlling all of the joints in that arm. This arm was optimized to do so. And it's arguable that we want to go beyond this. We want to involve the brain in learning to control high degrees of freedom. And there's a big question of how to do this. We have the hardware that's coming online, and we need to develop machine learning strategies to take advantage of this, right? And so here are quotes here. A lot of people agree, and these are old slides. Maybe I should remove the Musk quotes here. Challenge to design adaptive algorithms to maintain reliable and robust performance while continuing to improve over time is a major challenge. And another quote from Thomas Reardon, who's a co-founder of Control Labs, which has been acquired by Meta, is the mother of all machine learning problems. Okay, and so why is this, right? So I want to identify a few challenges for ML to be applied to neural interfacing. First is that neural signals are variable and noisy. Like it's biology, it's messy. Two, every brain is different. It's not like you can train a huge deep network on the average population, stick it in a new person and expect to have like magic learning transfer learning, I should say. Third is that neural circuits are not stationary. They actually learn. That's why this whole thing works, right? So you're dealing with a problem that you're trying to learn a two-learner sort of problem, right? As you learn to interact with something, it also learns to interact with you. And so that's a challenge as well from the machine learning point of view. And fourth, and importantly, there's very limited data. It's expensive to do a kind of like systems identification sweep on neural interfaces. You can't just probe all the parameters that you can, right? Like this is an expensive thing to overcome. So this is all that to say that on the face of it, it's not necessarily directly well suited for deep learning approaches, right? So we need to go back to other types of machine learning approaches that address these challenges. Okay, so what I want to touch on today is a few examples of work in that sphere from my lab. Happy to talk about, take questions on these as we go along, right? The first of which is optimization of intracortical stimulation for motor function recovery. Okay, so this is a collaboration with Marco Bonizato and Numa Dankos from the Polytechnique and the Université de Montréal, who both run experimental labs in this domain. So to motivate this, I want to say that each year there's about 15 million people that suffer from debilitating motor system injuries. So that's stuff like spinal cord, stroke, that leads to loss of motor function, right? And it turns out that targeted stimulation of motor pathways can actually speed up recovery, right? By targeting circuits that have not been damaged, but are weakly connected to what you want to do, you can actually kind of recover use of your hands, of your legs. And that's essentially what physiotherapy has been doing for years by forcing the movement itself. But it turns out that if you target the nervous system in a very precise way, you can speed that up tremendously. Okay, so this is a control problem. The idea here is you have an implant that interacts with the nervous system. You have the ability to stimulate the nervous system with a family of inputs, and you want to get targeted outputs. For here in this example is motor related, right? So here you have at your disposal a family of parameters that you can decide where to stimulate. the amplitude, like what type of timing your system, your signals are taking, and you want to get to desired target activations. And so the challenges here is that the parameter spaces are large. If you have large degrees of freedom in your stimulation paradigm, then the search space is big. And you have limited queries. You want to do this fast, right? And so the objective here, what we've been employing is an objective-based optimization where we want to target some sort of optimal activation or observable. Okay, so we've been using as a first pass, the good old tried and tested Gaussian processes, which have been quite useful. So just a quick point here about Gaussian processes. It's sort of a nonlinear regression type of schemes that actually gives you an estimate of uncertainty, which is quite useful when you're doing some space search, right? And so I know Gaussian processes have been heavily developed for geosciences as well. So the previous talk that has addressed using them in some sense as well. And so the experimental design I want to describe right now is basically that, trying to find a way to rapidly identify stimulation patterns to evoke specific muscle activations, right? So here you want to stimulate in the motor cortex of a subject, and we're recording the muscle activity of in the wrist of the subject, and we want to target activation of specific muscles at specific timing. So the way we do this is we've developed a kind of a novel hierarchical Bayesian approach that combines priors of Gaussian processes in a sort of sequential way to speed up this exploration. Okay, and so, for example, if I'm recording activity from two muscles, you can see here muscle recorded from EMG0, muscle recorded from EMG4. And we want to have activations separated by some time tau, right, as kind of a complex movement. Then we would like to, search the space of stimulation of an array that's been implanted in motor cortex to evoke these muscle activities. So if you use standard Gaussian process, typically this is the number of query points we need to get to a mean accuracy of about 50, right? But with our hierarchical approach, essentially what we do is we first fit lower dimensional Gaussian processes and then leverage the kernels that have been learned through Bayesian optimization to combine with higher order priors. And we do this iteratively. It turns out that you can speed up and actually get way better convergence on these optimization schemes, okay? So, and at the end, this is the true data. So you see we've evoked activity in muscle, the blue muscle here and the orange muscle here in ways that are differentiated. Like it's not like we evoke all muscles at the same time, and really close to the target that we've been aiming for here. Okay, so again, the idea here is that you build hierarchical kernels and you use them as priors as you build your Gaussian processes for the full thing. Okay. So this has been published as an algorithm in this paper here. And just recently, we've applied this algorithm to address optimization for natural movement. So this is a paper that appeared in Cell Reports Medicine last month, actually. That's the result of a long experimental journey where we showed that this algorithm can work online with natural movement, both in flexion extensions of a hand and also in a gait in a walking situation, right? And so I'd like to show you a little video here that shows this algorithm in working online in real time, right? So here, what you'll see is that there's a rat on a treadmill that has a spinal cord injury. So you'll see that the spinal cord injury is partial and the leg is dragging as the rat moves, right? And now the rat has an implant here in motor cortex, and in real time, we're tracking the foot elevation here. So now here, the previous example I showed you is we're tracking the activation of the muscles themselves. Now the observable we want to optimize for is something that's more complex. It's actually the level of the foot, right? And as we go along, what you'll be visualizing here in the bottom right is that there's a search of the parameter space that's done through this Gaussian process hierarchical algorithm. And essentially, this agent learns new combinations of stimulation through that array that leads to recovering of that gate, right? So you'll see here, we're tracking the foot elevation. We're selecting the best stimulation strategy that's timed with the gait of the animal itself. And then you can see that you've restored, you can see the difference between before and after here. Okay, so here, what's interesting here is that this is an injury in the spinal cord. It's partial, so there's still circuits that send signals to the muscles, but they're sort of unused, right? So we're recruiting new circuits in the brain that are weak, but by stimulating them, you can evoke you can recover walking procedure. And it turns out that if you do this long enough, then you're promoting these circuits to recover healthily too, right? So it's not like you need this to be on all the time. It's a tool for recovery. Okay, so in summary, right, for this part, right, I've shown you that Bayesian optimization with Gaussian process offer efficient online stimulation search for fixed objectives. We can reveal circuit computations, and it's easily scalable to more complex spaces. Okay, and I should say actually that this led to actually a Mila startup called Neural Drive. So Marco is the CEO of that startup, and so we're working towards bringing this to a clinical setting. Okay, how am I doing on time here? I'm good. Okay, cool, perfect. Okay, so I want to switch gears here and talk about treating disorders by modulating the peripheral nervous system here. Okay, so this is, speaking of startups, this is a collaboration with Mila partner startups here, BIOS, with whom we have ongoing collaborations, and thanks to MyTax and MedTech, which are granting programs here in Quebec, we were able to fund these collaborations, and we're really happy how things are going. And there's also some research that's done in collaboration with the Feinstein Institute here in this part. Okay, so here again, switching gears, the idea is that, as I mentioned earlier, there's a lot of things that happen in your body that are modulated by the nervous system, right? Cardiac rhythm, your breathing, a lot of metabolic function are mediated by the nervous system. And so a lot of pathologies that are linked to these functions can be addressed with neural interfacing, as opposed or in combination with pharmaceutical treatments. So one of the most popular ways to target this peripheral nervous system is by interfacing with the vagus nerve. So the vagus nerve is kind of the highway that goes from your brain all the way down and innervates a lot of your organs, your heart, your lungs, your liver. And so this is a part of the parasympathetic system that essentially links your brain to a lot of your organs. And it turns out that these stimulating the vagus nerve can have tremendous impact on a bunch of different diseases, and it's been in use experimentally for quite a while now. And basically, it involves very minor surgical implant of cuff electrodes along the vagus nerve that enable to record and stimulate the nerve. And so the challenge here is that you want to optimize different ways to interact with the nervous system, with the vagus nerve in this particular case, which is kind of a bundle of a bunch of different nerves. So it's kind of a deplexing type of problem. You want to be able to record activity from different fiber bundles that go to different organs. And you want to do this to not necessarily have sort of an online prosthetic that just stimulates all the time, but a first step is really to give recommendation tools to surgeons, to clinicians, to better tune these implants for targeted use. Okay, so the way we do this is again, in the same way we use Gaussian processes with Bayesian optimization to really optimize these interventions, targeting different biomarkers, heart rate, breathing, blah, blah, blah. And we do this pretty efficiently using Bayesian optimization. These are plots here showing that Bayesian optimization of these things actually do a much better job than doing some random search and some other kind of baseline stimulation tuning searches, basically. So this, what I'm showing here is a map in, for example, current and width of pulse stimulating this the vagus nerve, and we're measuring the activity in specific fiber bundles that are linked to specific biomarkers here, right? And on the left, we show the activity that can be recorded from different electrodes down the line. You can see that's kind of a multiplexed signal. There's different fibers that send information faster and at different depth. And so part of the challenge here is to decode which features of which of these activity patterns that we're able to record are linked to different biomarkers, right? So all in all, there's a big pipeline that's being developed to predict when certain pathologies are going to arrive from reading from the nervous system and how to intervene to optimally treat them, right? Within this pipeline, right, and so there are kind of other challenges, right? So if you have this pipeline, you're fitting some sort of stimulation parameter to an outcome. You might want to do this with online optimization in a new patient. That's great. We have ways to accelerate this. But in a sense, you're still starting from scratch every time you have a new patient. We know broadly that these things are similar across patients, but there's an opportunity here as you get cohorts of more and more patients that are implanted with these treatments to leverage this knowledge, right? So it's not exactly possible to do rapid transfer learning, but the question we've been asking here together with Stavros Zanos here, who runs a lab at the Feinstein Institute, and my PhD student, Chimeng Mao, is how can we accelerate personalization of stimulation protocols, given the fact that you might have a cohort of past patients that have been implanted, right? So what's important to understand is that there's actually a lot of variability across populations. So what we're showing here is experimental results from the Zanos lab that shows relationship between different biomarkers here, EMG amplitude, this is recording from a muscle, percentages of heart rate impact, and this is breathing data, so delta and breathing rhythms. And then we're fitting this to fiber amplitude, right? So if you're recording from a fiber in vagus nerve, you have a different impact on these different biomarkers. And then this is data in rats, and you can see that different colors have quite different fits, right? Generally speaking, you can see that here linear fits are better, here exponential fits are better. But overall, there's a lot of variability across subjects, right? So how can we navigate this in an efficient way? So what we want is, again, leverage this variability and similarities across the population to rapidly fine-tune an optimization strategy for a new patient. So you might want to start from a pool of population. That's a weird term. We need to change this. Pool of subjects. And then you might want to derive a population fit. What's the average fit that you want that fits the general population? And then you want to rapidly adapt this for a new individual in order to jumpstart your optimization process. And one way to do this is actually to leverage meta-learning ideas, right? Meta-learning I'm sure a lot of you are familiar with this, but here's a hasty overview, right? Meta-learning is basically a way of learning to learn. So if you have a system and you want to learn multiple tasks, for example, you might want to initialize a system in ways that it's easy to learn new tasks, right? So you might have a set of what we call meta parameters. This can be initialization, it could be optimization settings, in a way that multiple different tasks down the line can be learned faster. So the meta learning cycle here is choose these parameters, then optimize on different tasks, right? Task one here, this meta learning example is learning to dissociate different things in images. For example, dogs from music instrument in task one, and barrels from cliffs in task two, and so on and so forth. So the question is, if given these meta parameters, how can you rapidly tune the parameters in specific tasks in your inner loop to learn faster, in a sense? And so there's been a lot of research in meta learning for multitask learning and in AI in recent years. And the idea, again, is you basically learn in hierarchies, right? You want to optimize parameters that are good to optimize parameters. And it turns out that we can use these paradigms if you think about learning multiple tasks as learning multiple fits for different subjects, right? So what we've developed here is a way to essentially learn a meta parameter set, which is the set that's associated with the population, that best is rapidly learning a fit for a new subject, right? So this is the pipeline. I don't want to get too much into detail, but we initialize a model with this meta learned population fit parameter, and then we can rapidly, in the inner loop, use Bayesian optimization to optimize for a specific subject. And it turns out that you can fit even with very few shots. That means if you query your space of parameter with just 2 or 3 points, you can estimate a fit much faster than with traditional method if you didn't use the population. And even if you use the population, but with naive sort of transfer learning methods. So this is very promising. And we've done it in vagus nerve simulation, but this is an approach that's useful across many ranges of neuromodulation technologies. Okay, so we're really excited about this. These are results. Our different methods here, meta learning GP and meta learning regression do better. I'm going to skip this. You can trust me on this. And the summary here is that peripheral neurostimulation can be optimized via Bayesian optimization, which is a good paradigm to use, in my opinion. And meta-learning is a flexible framework for neurostim personalization, and we can be included in online optimization protocols across a wide range of use cases. So we have a paper that's currently under review on this. Okay, lastly, I know I have like about 4 minutes. I'd like to talk briefly about another collaboration that I have. And this time it's more geared towards scientific discovery. And that is surrounding the topic of identifying and guiding learning dynamics in the brain using brain-machine interfaces, right? And this is in collaboration with Dr. Amy Orsborn, who runs a primate lab at the University of Washington in Seattle, and my postdoc, Alex Payard here. And there's a few other people in my group working on this collaboration. And this is more of a readout task. So the 2 first examples I've spoken about is about stimulation, inputting information in the brain. This is decoding information to the brain to control external devices. So here's the experiment. That's quite a standard experiment in motor neuroscience. The task is that there's a screen presented to, in this case, a monkey, where there's a target in the middle, and there's 8 peripheral targets that light up randomly at different trials. And the task is to move a cursor on the screen from the center to one of the targets to get a reward. It turns out that you can teach that task manually with and then with the help of cortical motor implants, the patients can learn to control the cursor on the screen pretty rapidly. Again, this is a 2-degree of freedom task. It's quite standard now. If you read out from enough neuron in motor cortex, you can learn to control the cursor on the screen pretty easily. Okay. Now the question is, can we use these types of paradigms to really probe how learning happens in the brain? Learning happens in the brain. We have a pretty good idea of how it does at the level of synapses. We have good understanding of synaptic plasticity, but how this turns into learning in neural population is not quite well understood. And these BMI, again, the question is, what are the computational principles of learning in neural population at large that coordinate these plasticity mechanisms? And our solution here, our approach here is to use brain-computer interfaces, which actually give an unprecedented access to this learning paradigm. And by that, I mean, in any neuroscience experiments, if you're recording from the brain while an animal is learning to do a task, what you have is at best correlates, right? You're correlating the activity of your recorded motor neurons with, a reach or some sort of task paradigm. But there's so many neurons you're not recording from. There's a lot of stuff you don't know. You can't record from all the neurons. In a BMI task or BCI task, you have explicit access to the readout. What controls the stuff outside is only the stuff you're recording from, right? Because you're using that information to drive a cursor on the screen. There's nothing else. There's no spinal cord that leads to muscles, to whatever, right? Like you're directly recording exclusively from the neurons that are outputting to the world. And so you can ask questions, directed questions about learning in much better ways. You can perturb outputs of readouts and see how the brain adapts and so on and so forth. And this is the suite of experiments that we're developing here. And specifically, we're interested in the idea of co-adaptation. If there's learning that happens on the decoder side, say from a neural network, how are the representations that are learned by the brain to adapt to this learning going to evolve? Can we target certain types of representation, higher dimensional, more robust, by doing some interventions on the output side, such as regularization, using tricks for machine learning? These are all questions that are actually quite fascinating. Basically, how does regularization and tricks from machine learning impact learning from the brain? And we can address them in this paradigm. So the idea is to couple these the ideas from neural network theory with learning paradigms in neuroscience to probe really how the brain works and design these neuroplasticities to scale better, right? If you want to use these to control more degrees of freedom, you need to be able to understand how learning happens in the brain. That's the key. Okay, and I'm giving the signal that I'm close to the end here. So these are kind of the big questions we're looking after. What computations drive learning in populations? We use deep networks to probe this, and how sensory feedback inputs in multiple areas contribute to learning. So how do we integrate error through our senses? These are computation theory efforts, different programs that are happening in my group surrounding that project. We're trying to infer dynamics, learning dynamics from neural activity. We have neural theory of manifold and gradient learning based on data and theory that Alex has been developing. We have a preprint out there. And then we're also developing plasticity models to compare different bioplausible learning paradigms with what we can observe in the brain. Okay, so this is my summary. I hope I've convinced you that BCI technologies at scale are coming. They have substantial potential for impact, both in clinical applications, provide unique scientific tools, and also new ways to interact with technology and AI. And flexible AI ML approaches are needed for these unique properties. Namely, we have unique type of variability, non-stationarity, stuff learns, and co-adaptive paradigms between AI and the brain are kind of the key to many of these things, right? And I think some of the ingredients of these challenges are shared with many other application fields, right? So if you have an idea about how these types of ingredients can help you in one of your problems, come and see me. I'm happy to chat. And so with this, thank you. This is all the kind people that given us money to do this. And happy to take questions.
Maybe, I don't know if there's any questions online and please feel free to signal, but I have one question maybe on my end. But so you talked about at the beginning that it is coming, well, at the end as well, that it is coming, these types of technologies, but is the adoption of those technologies, how do you see the adoption of technology of this in general public or?
So that's a good question. So there's definitely consumer products, obviously on the non-invasive sides that are getting out there, right? Like we've been hearing about leaks that, like an example, we might know in a couple of days, Apple is pointing towards like AR glasses that have EEG electrodes in them, right? So these types of consumer grade products are coming. There's actually some folks involved in the Mila partnership, I think, like folks at Lucid are using these types of things. So that adoption, I think, is coming fairly fast. On the clinical side of things, there's and for good reason, but lengthy regulatory processes, right? The clinical trials are long. And so things are moving relatively fast on the research side of things, but in terms of deployment for treatment, we have to go through the processes, right? Like the same way pharmaceutical treatments are being developed. So patience is like, this is really deep tech, right? Like if you're talking about developing these types of technologies, you need to think in terms of, 10 years in advance sort of thing. But that doesn't mean that we shouldn't do it, right? Like I think there's a really high reward at the end of that road. So when I say they're coming, it's on the sort of clinical timeline that you need to think. Yeah.
And on it, because you talked about non-invasive on the side
Yeah.
of invasive. Is
Invasive, that's what I mean more. Like non-invasive, it's faster, right? Like you can think about, again, like EEG, use of EEG for menu control, whatever. There's also control labs, which is now a branch of Meta that uses peripheral signals like that bracelet I showed earlier. Essentially, it's remarkable how you can learn to interact with devices just by micro movements of your muscles, right? So you can record from the peripheral nervous system, i.e. from your muscles, and learn to be very volitionally control things like a computer and so on and so forth. So these technologies are rapidly becoming available. Yeah.
All right, do we have any questions online, Sophie? No, we don't.
All right.
Thank you very much, Guillaume.
Thank
Congratulations again on the associate professorship.
Thank you.
We might have a question actually for Guillaume.
I do have a question.
Oh, go ahead.
I've seen in this domain that these peripheral, like the bracelets you were talking about, it was difficult to interface. A few years ago, they were talking about even for a patient, after a few hours or a few minutes, the signal was changing.
Mhm.
So is it still this, or what you were talking?
Yeah, I think it's come a long way. And that goes to one of the points I was making, like co-adaptation is key, right? Like both as the patients learn how to use these things and as, the time of day changes, different days, there's drift, there's all kinds of different ways, right? So robustness in the coding algorithms need to be like really on at the top, right? I think there's been tremendous progress in the past few years, right? Most of it has happened, I think, through these big companies. So like transparency is not as great as in the academic circles, but definitely there's a lot of progress in the open source community as well. So that's changed. Yeah.
Okay, thanks.
Thank you very much. Well, thank you, Guillaume. Congratulations again on the associate professorship. So we're changing subjects. We're going a little bit more into robotics with our next presenter, Glenn Burseth. Glenn is an assistant professor, at the University of Montreal, a core academic member of Mila, as well as a SciFar AI chair and a co-director of the Robotics and Embodied AI Lab. There's a lot, sorry, a mouthful. His previous and current research has focused on solving sequential decision-making problems for real-world autonomous learning systems, or robots. The specific of his research has covered the areas of reinforcement, continual, meta, and hierarchical, I can't say that. Hierarchical learning, I'm sorry about that, and human-robot collaboration. In his work, Dr. Burseth has published at top venues across the disciplines of robotics, machine learning, and computer animation. Today, he'll talk about RL and robotics and design. So welcome, Glenn.
Yeah, thank you very much for that great introduction. Good to meet you all today, and I also very encourage questions throughout the talk, so feel free to reach out if you have any particular questions going through it. So yeah, today, robots have actually been around for a long time. They're very useful tools. They're already helping us a lot in manufacturing. They're already helping us a lot in fulfillment, being able to package items and types of transportation already around the world. There we go. Yeah, and sorry. Truthfully, they've been around for a long time. So this is a robot from around almost 100 years ago. It's one of the first humanoid type robots. So robots aren't necessarily something new, but the developments that have happened in the last couple of years have been really like applying machine learning to make these robots, have more of the skills that at least people start to have, like easily interacting with the world, being able to use visual perception to be able to act and even arrange things and perform some tasks. So I'll be talking about some of these improvements today, and then some of the things that we can even improve on a bit more. So the parts that are a bit, hurdles these days is they still, like current methods that don't use as much machine learning, they are a little bit, they operate in very controlled environments. Maybe you've seen some of the pictures where you have a giant fulfillment warehouse. There's no people in there. There's cameras and sensor systems pretty much everywhere. If one sort of thing goes wrong, the entire building basically has to stop working. So these systems are still pretty brittle in some of the ways they're designed. And it often takes, a lot of prescriptive behaviors and engineers to come and like program these robotic systems for a while. And this also introduces some other hurdles to using them. It means that before you even want to use a robot, you have to find a good robotics engineer that'll have any idea about how to use it before you start to maybe apply it to some of these other tasks. So how can we, at least, lower this bar significantly to be able to use automation more for the other types of tasks we're interested in? And there's a lot of benefits for this. I like to think of it as every person would have at least a bit more time to do whatever they want to do. I like to give at least this small example where like Einstein was working in a patent office. In his free time, he was doing mathematics because he loved mathematics and came up with things. Maybe it's this creative time that's where it's like the best time that we should try and give back to people, and that'll provide better benefits for society. You can also have a lot more agency for people as well, especially some older people. A lot of people are getting older these days. There's not as many younger people coming up to maybe take on some of the care that's going on. So robotics could help fill this area as well. But also I find that one of the tricky things, especially in terms of today's challenges, we're not very good at switching production. If we want to build an electronic car, minimum 10 years before you actually get to that point. You need a building that you plan, takes about 5 years to construct it, 5 years of iteration time before you actually get one car, and probably a few more years of actually making it better. This, at least from my point of view, is a little bit sad in our ability to adapt to the changes that we really want to be able to make. And robotics could help make these types of adaptations much faster. And we could be a lot more efficient with space. They're being used already to help grow some food better. We could have more vertical farming type mechanisms where we don't have to specifically design all of our tools to work for people. Maybe, robots can fit into smaller spaces, not have the same constraints, and avoid a lot of waste and have much better reuse. So the challenge is to be able to get to some of these in terms of like the machine learning that we have available today. Is we want and would need to be able to do all these more versatile robotic systems. This means that, basically everything that you deal with these days as well, you probably, maybe it's your first time visiting Mila, but you came in, you kind of knew that you'd sit down amongst the crowd. It's not very surprising how a chair works, even if it's a slightly different color than the other ones you visited throughout your life. But you want these systems to be as adaptive and, not as restrictive in the things that they can do. But I also, like in my research, want to go beyond just providing them sort of like work well in different rooms or in different tasks, but give them really complex goals. Even things that we don't know how to do. And I like to at least get to the point, I want to ask a robot at some point, is there life on Mars? And now I can go back to my creative time, or maybe I'm thinking about other problems, and the robotic system will figure out how to go about, constructing maybe an entire corporation that ends up learning how to launch rockets, how to do all the planning to be able to launch the actual system. In order there to actually figure out how to detect if there is any biological life on Mars, come back, give me the answer. Maybe quickly, at least in some time, but this would be the goal to try to get to. We want to be able to ask amongst ourselves and our systems questions that are more complex like these. And I'm actively doing a little bit of this as well in the Institut Courtois, where we're designing an automated, basically chemistry system to be able to just have it so that the scientists there can ask questions. I want to be able to produce this type of system. We can automate most of the manual process, maybe even some of the decision making. Okay, so getting into the tools that I've been using in this area and that I believe are really promising in here too, because they help solve what is basically a really complex sequential decision-making problem. We need to figure out how to make these things very flexible in the way they plan. So reinforcement learning is a great tool in this area because it allows agents to learn how to plan just from interacting. All we have to do is give them a little bit of an embodiment. They can go out and, collect a bunch of data, figure out how to do a better job at figuring out whether there's life on Mars over time. And it's nice because it encapsulates most of the machine learning system all in like this general paradigm. And as long as we can figure out how to adapt it to the real world problems better, we get to make use of this kind of simple paradigm that results in a great learning system. So basically you've got for reinforcement learning, you got an agent that goes out, collects some data in the world, it records its state information. The reward signal, which is usually what we use to describe, the behavior we want the agent to actually achieve. And then it learns to take actions in the world and slowly improve these actions over time. And these more recent days, the deep part of deep reinforcement learning has been very helpful. Now we can just pile into the robot or agent a lot of extra information, whatever it could be that's useful. And whenever it's going out trying to decide actions, now it can learn from the image observations that it's given or any other kind of sensory observation. In this state, now that I can identify better, this is the better action I should take. Update the overall network parameters such that the next time I visit this state, I at least repeat the action that was, overall looked better according to my reward function. So slowly over time can update this deep learning model to produce a lot of sequences of actions for planning that would result in higher value models towards those things for like being able to find life on Mars as an example for a goal. So this is a nice paradigm, but applying this in practice is where it starts to at least, expose a few cracks because we want it to be as adaptable as people are. But that means that it needs to be able to generalize better, and some parts of the system don't generalize as well. So what is sort of missing from this overall paradigm, and that we're like learning a little bit more from these days, is really though that we still don't have enough data. So we've been seeing probably that, language models have been able to be pretty successful because, they more or less borrow a lot of the good information from the internet. We've been kind of very nicely piling the 20 years of all of our best thoughts into the internet. Now we can create a system from that that's somewhat intelligent. So maybe we just need to spend the next 20 years collecting a bunch of data. Basically, you could record people, the things that they're doing to show that they're actually doing things that are smartly, and then be able to train a robot system from this. And it should be able to generalize. And it's also important to have like good diversity. So I'd want like data from everyone in the room really nicely to see how you all perform tasks differently. And that gives it this sort of more adaptive behavior as well when you've got that much diversity. And then what do you do if an agent, I guess, previous more like language model based thing is collect a whole bunch of data, freeze that. What if you run into a novel situation, which we do every single day? Just apply reinforcement learning. It's the literal system for interact with your world, increase your reward function, and just keep going from there forth. So I'll talk about a few ways to be able to apply this to a couple of different applied tasks. So the last part is like now just trying to get this to work more in the real world. So here's a video from one of the earlier DARPA tasks of working on getting humanoid robots to do things that are more or less related to being able to recover from some disaster situations. You can train in simulation, but those aren't always well designed for certain tasks. It takes a lot of work to make a simulation too. So in some ways, the difficulty we go in creating the simulator, we might as well just work on collecting more ground truth data that's actual fact in the real world. And then we can use that to build on these systems. And we just need to figure out how to incorporate this data into these systems. So the last kind of interesting caveat is we're talking a lot about data. And when we're doing large language models in those cases, there was a process where they skimmed the best data from the internet. So we also need to be more kind of considerate about what that kind of data should be. So in this case, is it enough to collect any type of interaction data? You can think of a robot arm here isn't going to know much about navigation. A car, isn't going to know much about actually manipulating things in the world. And this amoeba here is a great example. It's kind of got a very small world, doesn't have many tasks. So it's not going to have a really large breadth of things it's going to have to learn. So there won't be a lot of great information inside of the data set. So intelligence also has, some kind of strong connections to the morphology of the actual agent that's doing these things. So these are not great examples. We want to get back to this Einstein type robot that, you know, can sit, do math, and most of the other things that people would probably be able to do as well. There's also sort of a few fun caveats where it's not just a humanoid robot. You know, many of them need to also have some of the important features. I kind of like to point out this one for Boston Dynamics. It's a great biped, but it has no hands. It's got basically fists. So I don't expect it to cook me dinner nicely or anything like that. You still need portions of this full system in order to collect all the data that we would like. So can we get a robot to start to do most of the tasks a person could? All right, so here I'll talk about like one of my first, or at least the first project I'll talk about today, is about trying to kind of drill down more onto two of the concepts here. We want to collect more data, and we want a system that like both navigates and manipulates stuff in the world. And in this case, there's basically no supervision that's implied in this project or used from the people. As long as we make this robotic system, we put it down in some room, over time, it just learns to clean the room. It takes about a day for it to learn how to train. And then, so some of the like methods that are used here is basically, you can take this now system, and the morphology is fairly important. Start by training it to grasp some objects. So we basically put it in the room, put a pile of things in front of it that can learn to grasp, and basically give it some time just to practice. It doesn't drive around as much. And then once it starts to get some grasping ability, then we just kind of turn on the navigation part for the overall agent. And now it can actually go around, grasp things, learn up how to clean around in the room. And what really helps in this case is actually being able to allow it to train here in open space. So there's a lot of some hangups for applying robotics. Actually, if we just change the task a little bit such that it doesn't have a few of these resetting issues, now it can go along collecting and make some progress towards collecting this internet amount scale of data that we would want to train these agents from. So the reason why this is also nice is machine learning systems, you know, as long as you give them more time or data, you know, they tend to beat out a lot of expertly designed systems. So here, this is just, you know, the robot after it's trained for a day inside of this room on its own can run around in the room, clean up all of these little, in this case, they're balled up socks that were used as basically trash that's inside of the room. And if you give it enough time, we basically grabbed a version of a controller that was like the best expertly created thing we could think of, spent a couple of weeks making it. But if we, you know, it took us 3 weeks to make the scripted controller and 2 days to train the learning one. So if we get to this scale part, then we already start to get the better advantages from learning. And we can just take this robot and put it in any other room without having to do any more kind of crafting of a sensor system, and it can still keep learning to do this task there as well. Okay, so we've got some good components where we're learning from large scale data already, but we also want to learn some more useful structure. And this is the part where we want to be able to generalize better. So that previous project learned in a room from scratch, but what can we transfer? It'd be nice to use the data that was also learned there and use it for other tasks, where we can automate this process to be able to collect more data, but it's also good to find better structured policies. And one way of thinking about doing this is you could make like more of a goal condition policy where I would, you know, give this picture, sorry, hopefully you can see this on the right to my robot, you know, please clean my room. This is the current state. I want it to look like this, which is much better, much more clean. And now you can have it just generalized to different rooms and give it different pictures and have it be able to clean. And you want to be able to like learn this causal model across these different goals. And you can do this using machine learning and deep reinforcement learning as well. Some of the caveats are you do need to generate some additional goal data. So if you don't happen to have access to a bunch of clean and dirty rooms, you can use a model to generate basically clean and dirty rooms. So collect a bunch of data from the internet. Now you can generate what looks like clean and dirty, feed those into the policy, and then put it in an actual room. And you just need to provide one clean picture of your room. Hopefully everyone in here at least has one picture of the room when it was clean, and then you can use that to be able to, with this agent to help it clean. Okay, so one of the last challenges is dealing with the problem of, you know, when you collect data on a robot, even on the one was in here, it was on that specific robot. You know, we'd like to be able to make better use of our data so that's not specific to one individual robot. I'd like to be able to like train a robot arm and then also train a different robot that can just walk around, glue those two policies together, and it should basically be able to learn from that. You've collected a lot of data on how to solve these different tasks. You shouldn't have to collect wholly new data on the combination of these two robots. So this is the next work that I'll talk about. We're gonna learn, via some large scale interaction, how to train a policy, one single policy that basically figures out how to control all of these different morphologies in the simulation. And we don't need to provide much information basically to tell it what the morphology is. So from here, we're basically going to use a transformer model, and we actually construct it basically such that you can send in a bit of information to the model, which is kind of a really rough approximation for what a description of the actual robot is. Kind of something as simple as, it has 2 arms, it has 2 legs. That's all the information you need to know. Now you can go perform the task. So this has been really helpful because now it allows us to generalize across these different robots. So if I have a different robot or a different agent, I can give a bit of a description and include the data from that robot into this model as well. And this also gives us some great progress in terms of generalization. So if we hold out a bunch of different robot designs and then ask them to, in this case, ask them to do some generalization to these new ones, we get fairly good performance in terms of how well it still gets reward on these tasks for an entirely different morphology for an agent. So it could have like less arms, more legs, different joints, and it's still able to map to these types of generalizations. And in this particular work, we were trying to get rid of having to assume a lot of the information about morphology. Because usually in a robot system, you have to have an engineer again, carefully program the actual design of the robot, where the links are, their lengths, their weight, provide that to the model. In this case, we're able to train the network and just feed in a version of a state representation. And then from that, it learns just that, actually, how to infer what the morphology is and how to control the agent from that. So the only thing we really end up having to do is a bit of a tokenization of the state. We feed this in as if it's a sentence, and then the ordering and description basically allows it, okay, this must be the ant robot with 4 legs or 5 legs this time, now that it has some extra joints than what it had from before. And we're also starting to see, if we at least look at some of the stuff in the transformer model, it's learning a very sparse attention. So it is figuring out like which joints actually connect to other joints, which ones you can ignore, and which ones end up being important for actual actions that come out of the model. So it's learning essentially, it's learning that wiring system for the robot's design internally. Okay, so the last part on this is I'm going to talk a little bit about task generalization. So I talked a bit about goal conditioning. We want to think about how to give tasks to our systems, and these perform a lot of planning. So in this case, I talked about this goal conditioning problem, but I asked the robot in that example, clean the room. There happens to be a window in the back of this room. Does this mean the robot should also go outside, reconfigure the entire planet back to the time that was in that image? Because that is what I told the robot at the time. This is not what I meant. At least I'm pretty sure it's not what I meant. But it was pretty late for that deadline. But basically, it could be really nice to be able to replace some of these things with text. Images tend to over-specify problems. Text tends to under-specify the problem, but that gives us more freedom to do things. So if we can use more natural goals, we can just say like, go clean the kitchen, things like that. I don't need to provide an image now, which is nice because we can get away with ever having to have our room clean now, as long as someone else cleaned their room. And then now we can reuse this data. So we want to get now to tasks that we don't know much about. So this is helpful because like a large portion of things we apply machine learning to is things we already know how to do. But I'll go through this a bit quickly. We want to get to the point where like we want to ask a system, design a more efficient battery, or one of those questions, is there life on Mars? More general goals. So in some recent work, I've now been like applying this overall to being able to find really high, like really useful molecules, either for drug discovery in some ways, or also for manufacturing design. And this becomes this version of actually specifying a problem. In this case, we're going to rely on text a lot more too. We're going to take the original, basically description, which is usually graphical over here, sorry. For the actual molecule, we can convert those into text thanks to a couple of new libraries, which means we can try to take advantage of the text that's available on the internet or these large models, and then be able to use transformers to be able to train a good text model to perform RL and use the big hammer that is deep RL, basically, consume a lot of data, perform a giant search over all the possible combinations of molecules to try and find better ones. And really what we tried to pull on a lot in this project is taking advantage of data sets that use text. And there are some large ones for molecules as well. In particular, we targeted like molecular docking and a couple of other tasks for being able to do different types of molecule design. And the results that we get, I guess, if you're more familiar with, there's also two kind of grammars that you can use to describe a molecule in text. So we do some comparisons between those as well to see how well these grammars mesh basically with search and deep reinforcement learning, the tools that are available. So basically, it's a combination of many things. We've got selfies and some grammars for trying to figure out good policy architectures in this new type of design space. And how big we need to have these models to be able to consume these large amounts of data, and then also do some exploration according to different reward functions. So we find that, in terms for one kind of group of tasks that is more diverse, we find that using the transformer models that we train, we pre-train them on language and some molecular data, and then we use reinforcement learning to improve the performance, work really well on a lot of these tasks. For some of the docking tasks, the transformers don't perform as well. We're still investigating that one. We think the docking tasks are really specific and not as related to the data sets that we have available from basically molecules as text. So that's sort of a future area of research. So this is sort of where we study different data sets and how much they increase performance. And interestingly, the ChemBL data set ends up being fairly helpful for being able to train these models, partly because that data set is a bit more diverse. So we've got these giant data sets of different zinc molecules that go into the billions of basically points, but it's not a very diverse data set. So we need that diversity back again to really take advantage of these large models. Need diversity, need multitask information. Okay, so there's some connections between these, but maybe I'll go through and pass on these for now, just so we can ask some other questions. I'm also I'm designing my lab as well to kind of hammer in more on this multitask learning part. A bunch of data from a bunch of different robots, create one model that'll control pretty much them all. Great, and then basically that's the overall talk. And if you have some additional questions, I'd be happy to answer them.
Thank you very much, Glenn. Any questions in the room or online? No, but thank you for the reference to, I don't know if it was intentional, but Lord of the Rings, to one ring to rule them all.
It's a good ring.
It's a good ring. I would hope so. Thank you, Glenn, so much for your presentation. For the robotics summer school, maybe you want to say a few words happening in 2 weeks, I believe?
Yes, I mean, for those that are interested, we're organizing a robotics summer school. The aim is to help kind of two directions. People that are more machine learning people get more familiar with robotics, and people that are more robotics people get more familiar with machine learning. And then together, we could help, make more progress, learn some more about these new skills, and be able to grow some of the process of even collecting this data and advancing robotics and automation for the future. Great, thank you.
Thank you very much. So if you have any questions, you can contact us or Glenn directly, but you can contact us in the partnership team and we can put you in contact very quickly. But
Yes.
Thank you so much, Glenn.
Thank you, everybody. Take care.
Our last talk of the day, I'm passing over to a different kind of project that we have. I believe some of the people that were here yesterday heard talk about the AI for Humanity team. One of the projects that they have is Project DISA, and the Project DISA team is present today in hybrid mode, so here and online. They're joining us as a team. DISA is data-driven insights for sustainable agricultural. It's mainly focused in Rwanda, in Africa. We have, I believe, 3 people joining us. So we have Alison Cohen, who is the Senior Applied AI Projects Lead at Mila. In this role, she works closely with AI researchers, social science experts, and external partners. She's part of the team of the people that presented yesterday, more generally Trail and Responsible AI. Ernest Anamikaze, am I saying that right? Hanavakize, sorry, is project manager at Future Earth and McGill University, and Jennifer Gerard is deputy director at Future Earth. So the floor is yours. Thank you very much.
Okay.
Thank you.
Perfect. Allison.
Perfect. Can you see me and hear me?
Yes, we can.
Great. I'm also hoping I can request that Daoud also be promoted to a speaker. He's here as well and part of the team.
Oh, good.
Thank you so much. So first of all, thank you all for being here. I'm so excited that we get to present this work to you. Charles, you did a fantastic job of giving a little bit of information about me and my background. So I'll just mention that DISA is one of the projects in the AI for Humanity portfolio. And the reason that we're so excited to be presenting it today is because it really showcases so well some of the high impact work that we're doing within the AI for Humanity team, but also the ways in which we are collaborating with a number of external stakeholders to bring these projects to fruition. And with that, I'll pass it to one of our collaborators, Ernest.
Yes, thank you very much, Arson. So as they have said, my name is Ernest Habanabakize, and as they said, I'm a project manager at Future Earth. And today we're going to be talking about the data-driven insight for sustainable agriculture. So first of all, why should we even care about farming, right? So there's now 7.9 billion of Earth that actually depends on land that is really degrading because of the use of conventional chemical-driven agriculture systems as opposed to sustainable practices. More specifically, actually, 65% of the land in Africa is degraded, and that has actually led to 30% decrease of the yields since 1961. And but as you can see, there's hope. If you see the image here at the left side, the soil is visibly more aggregated. With soil aggregate that very stable and very together, as opposed to the image on the left that look more oozy. That means actually regenerating the soil. And what that means is more capacity actually to retain water, more capacity to actually put more microbe that are beneficial to the soil, to the plants together in the soil, and more water retention. And that's the reason why today we're going to be talking about regenerative agriculture as one of the potential solutions to this massive degradation of land due to the use of chemical use in agriculture. But what is exactly regenerative agriculture? Where even if the term has recently gained actually a lot of talks from the media, from the public, academia, there's no common agreed upon of definition of that term. We tend to see actually scholars having a common understanding of the definitions that are based either on the practices or the potential benefits or outcomes, or actually the combination of the two. And this becomes very important because as stakeholders or as people who are working together, we need to have a definition that actually we agree on as participants or as people are on the project. And for us, after consultations and exchange knowledge between our partners and people in the group, we see regenerative agriculture as a mode of farming that transition away from this chemical-driven system of farming that degrade the soil, and then transition to actually the system that breed the soils to a nature positive, net zero low carbon emission that actually promote best practices. And we actually base our definition on the 9 principles. And when I talk 9 principles, they were taken from one of our partners in India, Andhra Pradesh. That's a community of 800,000 farmers who have transitioned away from chemical-driven farming to regenerative agriculture farming over now 10 years. And they are becoming a very big success story around the globe of the benefits they've seen so far. And so some of these principles, they are now 9. I'm not gonna go into all of them, but I'll just give you a quick overview of the 3 of them. For example, when you talk about crop cover, what do we mean? So it's really ensuring that the soil is covered 365 days a year, or at least as much time as possible over the year. And that actually ensures that when the rain falls on the soil is not degraded or the soil is not destroyed, and there's better infiltration process of the water in the soils. And that's some of the benefits I can easily say for now for the crop cover. And when we talk about things like crop diversity, it's really ensuring that we have as many species as possible in the farming systems. And what that really means is actually those species being grown close to each other, bringing the mutual benefits of the interaction of those plants to that very soil, and then ensuring that the microbial community is doing well, and actually each plant bringing a set of benefits to the pumping a set of benefits and microbe to the soil, which become part of the whole system as the system as a whole. And so when we talk about no or low tillage, we're really talking about trying to minimize the disturbance of the soil as much as we can, because the more we do the plowing, actually using the hoe or the machines, the more we destroy the fungal structures that glue the soil together, so that we actually can get to the structure that I've shown you in the first image. And you know, when that structure is destroyed, so the microbial diversity and the content of the soil get distracted, and you know, the structure of the soil get loosey, which actually leads to not enough capacity to hold the water, and actually many more other losses can happen because of that. So really, all of these all these practices means to ensure that we have better soils, health soils, and then health plants. And more health plants we have, the better soil we have as a feedback loop. We have some reference, some literatures that people can go to get more details about these principles when they can. So, but what's the goal of this project? So one of the biggest problems that regenerative agriculture is facing these days is the adoption, and actually because of the lack of evidence, the data of the benefits. So as I said, there's still a lot of confusion about the definitions. You know, some people based on the practices, other people based on the benefits, or both, which really calls to the fact that we really need to have the evidence for adoption. We are in a context where for the last 10 years, governments, academia, and public sectors have been promoting chemical-driven agriculture. For really that to change, we need to have a base of evidence to prove to people, so that people can change the mindset or the policy action. And for that, we try to leverage the use of technologies, local knowledge, ground truthing data to build machine learning models that can help to build those evidences. And what we hope to do with those evidences of this data is actually to motivate policy response, you know, at all levels, in terms of the decision makers, in terms of the policy actors, and actually at farm level, so that people can act based on these data. And eventually, in terms of research, we plan to do some comparisons of the benefits of the viability of regenerative agriculture across the domains, you know, in terms of environmental benefits, economic benefits, and social benefits. And eventually, in the long run, build the capacity of the farmers and the local communities in Rwanda, who are eventually going to help the adoption at the scale of this practice. But I'm going to pass this to Arson to really explain more on how we're going to do this and how we do this using technologies and local actors. On you, Arson.
Thank you so much, Ernest. So as you can see, we took a very careful approach in defining our goals. Once we did, we assembled a very strong team, and then we aligned on the methodology that we would take to conduct this work. Once this was done, we decided to go directly to the field. We wanted to understand more about what regenerative agriculture actually looks like in Rwanda. So we conducted a survey of over 800 farms going around the entire country to better understand exactly what it is that these farmers are doing. And we did this for two reasons. One is so that our definition of regenerative agriculture could accurately reflect the way that regenerative agriculture was being practiced. And the other is that we have data at scale. We've gotten data at scale through satellite imagery via a partnership that we have with an organization called Planet. And if we are to use machine learning models leveraging this data set, we need to know that what we're observing from the sky aligns with what we're seeing on the ground. So this was a way of establishing ground truth data that we could use to cross-reference with our satellite data. And of course, our goal on the machine learning side is not just to be able to identify regenerative plots of land, but to demonstrate the impact that regenerative agriculture is having, specifically in terms of the impact that it's having on the health of our soils. So we made sure to ask farmers about things like soil erosion and soil fertility and other metrics that would allow us to really correlate the impact of these farming practices with outcomes of interest. And here you see an image of one of our collaborators in the field speaking with one of the Rwandan farmers that we had interviewed. And with that, I think I'm passing it off to Daoud.
So thank you, Alison. And I think you've laid a great foundation. And as we said, we surveyed 815 farms all across Rwanda in our first phase for a two-pronged approach of pairing the data on the ground from the farmers as well as satellite imagery. And we have a diverse spread. On the image, you can see the survey locations, as well as what we built. We built a regenerative score through various questions that we asked. These questions were largely anchored to the practice, specially defined by Andhra Pradesh and built by domain experts, and help us figure out how each farm is doing on the regenerative context. The questions about the 9 principles, like crop cover, or how many species are planted, is a tractor being used? So questions that tackle to what extent the practices are done, as well as questions that relate to the context that is there. So for instance, we ask how eroded is the soil in the current status quo, the water access. And finally, we ask how long has this been going on? So we can measure the change over time when we come to our satellite images. And so together with some of these questions and with the satellite images, we believe we have something quite exciting. Can you have the next slide? So I think the thing that makes me the most excited about this project is the new frontier that we have in remote sensing. And this is something that's changed drastically over the past couple of years even. And this is the advent of new high spatial and temporal resolution, which really is groundbreaking in this field. So we have data at the 3-meter resolution almost every day coming in. And what this allows us to do is to monitor the growth, the harvest, and the entirety of the farmland throughout the year with our imagery. And especially considering the nature of smallholder farms and individual crop fields, which is an novelty that we want to do. When you have a crop field that's 20 meter by 20 meter, and when you have previously we used to have 10 meter per pixel, it was very hard to see what's going on. And fortunately, now we have the pair of both 3-meter resolution at the daily level, as well as one snapshot at the 0.5 meter, half a meter resolution. And this makes a very clear image where even visually you can very easily see what's happening in each field. This allows us to have build models and really apply computer vision on this data set in an unprecedented way as ever before. And then from that, I'll go over to the ML avenues. So now that we have this great source of data, the question is what is the best way to make use of it, and what are we trying to do? And one of the main things is, what are the regenerative practices can you monitor from the imagery itself? And I think from the first low-hanging fruits we're thinking of tackling is the crop cover. So can we detect, if we know the exact position of a crop field, can we detect if there's crop throughout the year? And as well as how many species are there in a certain area. This is increasingly challenging as adjacent fields sometimes might have differing or varying crops in them. And this brings us to a very open problem, which is delineating where a field is and is not, is very tricky and unsolved at the current moment. So there is no, so to speak, segmentation model for crop fields. But this is one of the most exciting avenues of research that we have right now. And we are hoping that in a combination of three things, one, the high resolution imagery that we have. So for instance, at the 0.5 meter especially gives us the clarity to infer boundaries. And the temporal information that we get allows us to build up priors that we can pair with some novel advances in zero-shot segmentation, like segment anything. Together, we can be able to build better models for field segmentation. And once we have that, we're hoping that it can unlock some of the other things. I think this whole field is kind of unique in the sense that we have a very large amount of data and images, but the challenge is still we want to move in a way to really scale our findings. We need to move in a way that the labels are still like low cost. And so with this challenge of large amount of data but expensive labeling, it's a very exciting avenue for unsupervised learning and even self-supervised learning. And that's the third avenue that we're very excited about. And finally, we want to investigate further what measurable outcomes can we see from satellite imagery towards the impact of the outcomes of regenerative farming. So for instance, we can see, because of the temporal information, measure when adverse weather events, things like drought or excessive rain hit. And we can see whether farms that carry out regenerative practices sustain the levels of agriculture there or are adversely affected compared to neighboring farms. Similarly, we want to be able to compare the harvest quality, and we can measure this as well, hopefully using crop indices. So overall, I think there's a lot of open questions that we're trying to address. And it's a booming area with this unprecedented imagery as well as advances in computer vision that has happened over the past years. Okay, with that, I will give it to Jennifer.
Thank you so much. My name is Jennifer Gerard. I'm the Deputy Director of Sustainability in the Digital Age and Future Earth, so partners in this work. So it's clear that the work that we are talking about today can't be accomplished by any one group, one organization on their own. And as you can imagine, it's not always easy finding ways for such a diversity of groups and coming from very different levels of domain expertise to collaborate together. So what we started with as a foundation was really building on our previous work in this space. So the Reimagining Climate Governance framework, which you can see on the screen, was initially conceived actually in the context of changing the way that climate projects are funded broadly. But we realized very early on that the applications of this framework in terms of co-developing very bottom-up participatory innovative solutions are very far-reaching. And so some of the main aspects from this framework that we integrated into the DISA project from the very earliest stages are ensuring that we highlight not only what worked well in the project, but we also highlight what didn't work. What are the main challenges? Where did we fail, essentially, so that we can actually fail forward, learning from our mistakes. We also really focused a lot on building trust, essentially. So taking a co-learning approach, iterative approach to developing solutions and really testing along the way so that we can learn more about each other's disciplinary approaches. We also took the time to really iteratively explore, exchange ideas, exchange knowledge bases as a team. So this includes weekly meetings with the core project team that have been going on for many, many months. And we ensure that all the solutions, all the ideas and research avenues that we're developing are really strongly rooted in the local context. And that is to say, in the context of smallholder farmers on the ground in Rwanda. And the reason is we want to make sure that ultimately the solutions that we develop through this project are reasonable or appropriate to integrate locally so that we can have that impact. But also we see that as key ultimately to scaling the research project, so to expanding into other areas. Members of our core team have also fostered knowledge exchanges. So between farmer cooperatives in Rwanda, who we're working with on this project, and farmer organizations in Andhra Pradesh, which my colleague Ernest had mentioned earlier, the Andhra Pradesh Community Managed Research, Natural Farming Initiative, which has really been a huge source of inspiration for our project and with whom we continue to collaborate and learn from. In terms of collaboration within our team, we've taken a very participatory approach from the outset, as I mentioned, building on trusted relationships. So really what we've done is try to identify right at the beginning what those key problems, the key research questions we want to address are together. So in a very interdisciplinary method. So that involves, of course, learning about each other's disciplinary backgrounds, building sufficient understanding to really be able to ask the right questions of each other. And of course, being accountable to each other, to the other members of the project team, and to our partners on the ground. So DISA is in line with the theme today, built on very strong partnerships. The core group that you can see here includes, of course, Mila, who are, as Dawood mentioned, so eloquently leading on machine learning and data analysis for the project. Of course, sustainability in the digital age and Future Earth, the organizations which I am affiliated with. And we're really leading on partnerships, fundraising, and providing that agricultural domain expertise. We also work closely with the Regional Research Center for Integrated Development in Rwanda, RCID, a local organization who coordinated the ground truth data collection that Alison described. Leaper Labs, a Rwandan organization that focuses on providing opportunities to learn, develop, and deploy tech solutions. And Planet Labs, who Alison mentioned, provided the high resolution satellite data. I also wanted to note that we work with a wide variety of other organizations as well. So just to name a few, we're in contact with Bridge to Rwanda, an agricultural organization in Rwanda who participated in those knowledge exchanges I mentioned that took place back in 2021. And now, actually inspired by those knowledge exchanges, have over 100 demonstration plots actually testing the viability of regenerative agriculture in Rwanda, which is really exciting to see. We have collaborators in C4 ICRAF as well, the World Agroforestry Research Center, with whom we're exploring novel methods to actually test soil organic carbon, soil carbon sequestration. So seeing how this might relate actually as an outcome variable to climate impacts and climate mitigation. And of course, the Andhra Pradesh Community Managed Natural Farming Initiative. So really, again, a critical partner for us. And I want to leave you just with a little idea of the wide range of affiliations, geographic locations, backgrounds of our wonderful team of collaborators. So of course, the Mila team, so you've heard from Alison and Daoud, who are here virtually with us today, as well as Gaetan and Melisande, who are part of the Mila organization. We have Rosette, our intern at Leaper Labs, based in Rwanda. We've got the Future Earth and Sustainability in the Digital Age team, our director, Micheline, my colleague, Ernest. We've also got Aaron, Poonam, and myself. We have, of course, also the core team at Regional Research Center for Integrated Development in Rwanda, RCID. And that's really led a lot by Ramsey and Jules, who are based also in Rwanda. We've got senior GIS experts who are located on the ground in Rwanda as well. That's Casper and Connie. Kinsey, who is our main contact point and close collaborator at Planet Labs. And of course, our colleague Jane, who's joining us here today, who is doing an externship with us at Future Earth, but who is based at the Open Air Network and came in from Ottawa. So we're grateful to have her with us today. And Eliane, who is at C4 ICRAF now, but was previously with us at Future Earth, Sustainability in the Digital Age, and who is really one of the people who ideated this in the first place. So of course, grateful to her leadership, her thought leadership, and her vision in this project. With that, I will hand back to Alison. Thank you.
Thank you so much, Jen. So I'll leave you with the idea of how you might be able to engage if there is interest among those that are here today. This is obviously a pretty significant project, and we couldn't do it without the help of such strong collaborators. So if there is interest, the areas that we've identified as being the most high priority for us is, first of all, of course, financial support. This is what would keep our project going. We're doing well for now, but we do know that we want to be deploying this work and be involved with it long term. So financial support is going to be incredibly important. It's going to continue to be important. The other way you can collaborate is, as Daoud mentioned, we're working on highly cutting-edge scientific work. So if there is interest in becoming involved in some of these new research domains, specifically leveraging high-resolution satellite imagery to do things like delineate specific boundaries or to identify things like crop diversity, that those are areas that we would be quite interested in collaborating on. Just so that you know some of the long-term goals of this project and areas that we might otherwise collaborate in more in the long term, we're hoping to develop an app that farmers will be able to use to continue to provide us with real-time ground truth information, and so that we can provide information back to those farmers so that there is a consistent exchange of value. If there's expertise there, that would be of interest. And then finally, our goal is to continue to develop this project in a way that actually can be scaled outside of Rwanda and to other countries around Africa to promote the regenerative agriculture farming model as broadly as possible. So if scaling up is something that you specialize in and would like to support with, that would also be something that we would find quite interesting. I'll just say, if you pass to the next slide, Jen, this is my contact information as the project manager representing Mila. I would be your first point of contact, so please don't hesitate to get in touch. Thank you so much.
Thank you very much to the DISA team. If we do have questions, we have time for some. Online, is there anything? Perfect. All right. Well, thank you very much to Jennifer, Ernest, Daud, and Allison for the last talk of the symposium. It officially concludes the symposium, or our 2023 edition. It's very, very interesting to see all of you here, see all of you online as well, to live it. This was our first iteration since the pandemic, or pandemic effects, I should say. So we hope to do it, well, we are going to do it next year as well. Maybe some change, maybe we'll keep a similar sense, but this shows you what kind of research that we have here at Mila, and it outlines all of the different disciplines that we're doing, and not just we're doing our own thing in AI or in ML and DL, and we're not communicating with the outside world. I think the strength that we have here is a lot of the relationships that are being built between the researchers, between the students, but also between the partners that we have here, that we've had here for the last 2 days. So I want to thank all of our presenters, our speakers that had great and fascinating research to share with us. I want to thank all of our partners who participated in the last 2 days, our internal teams as well that have organized the event and also helped us to organize it, or participated in having a lot of contacts with most of us. And we do hope that if you have ideas that have been sparked by this event, by the talks that you've heard, if you have questions or you want to go ahead and connect with us and learn a little bit more about how we can collaborate, or just have a crazy idea of saying, well, can we do that, and have something of interest with what we're doing here at Mila, please feel free to contact your account director. If you don't, you can send a message. If you don't know the account director, you can also send a message to the partnership team in general, so partnerships@mila.quebec, and we'll be happy to answer and really try and have a good collaboration and fruitful collaboration in the future. So please keep in touch with everything that we're doing, because it's not the only event that we have. We talked about the summer school for robotics in the next 2 weeks, but we're going to have a lot more events coming throughout the year. We had MOML, so a molecular learning conference on Monday as well, and some of the partners were there, UCAM included. So please be aware of what we're doing, and it's our great pleasure to welcome you here every time we have an event, or every time you send us a message. We'll very, very gratefully respond, and we're very eager to have a lot more conversations about all that research. So thank you, everyone. And if you have any concrete collaboration ideas, don't hesitate to contact your account manager, as I said, or contact us. Have a great rest of the day, and see you next year.